I'm Thomas Bitoun. I will be chairing today, this morning session. So the first speaker today is Professor Meng Chen from Fudan University and the Shanghai Center for Mathematical Sciences. It's a great honor to have him speak here. He's held numerous distinctions and is a world-class leading expert, famous for his work on birational algebraic geometry. Today we'll talk about on varieties of general type with many global holomorphic forms. Let us welcome him now.
Okay, first of all, I thank the introduction. And it's a great pleasure to talk about my recent result here. And thanks very much to the organizers for the invitation. So today, this is a topic on the explicit aspect of birational geometry, especially induced by global holomorphic forms. So this is this lies on the classical aspect. Yeah. So I start with introducing basic notations and background. Okay. So so first, so let me start with the base field is a complex number field C. So of course this works for any algebraic closed field characteristic 0. And so so here I only consider varieties of general type. So general type means there are many equivalent statement for general type. So first let me so first, by the minimal model program, so given a variety, we start with a smooth projective variety V. Then by MMP, so we know that there is at least a minimal model X. So the minimal model usually has some mild singularity, but the point is the canonical divisor Kx is naive and big. So in general, the X is the canonical sheaf is not a line bundle. Maybe it could be some multiple of or some tensor product of this canonical sheaf is line bundle. So usually we call it Q divisor. So so there is the most important birational invariant. So which might we can see, study the canonical volume. So there are another way to define, but here, since we are considering the minimal model, so this is a birational invariant. This is nothing but the top self intersection of the canonical divisor. So usually this is a rational Q number, positive number, and we say that X is of general type. It simply means it's positive. Otherwise, it's actually, from definition, it should be 0. So today, I only concentrate on the varieties of general type. That means those varieties admitting a minimal model with positive canonical volume. So in lower dimensional case, for example, for a Riemann surface, for algebraic curve, smooth algebraic curve, so the general type means genus at least 2. For surfaces of a general type, during the Italian group. The classical theory says any smooth algebraic surface admits a smooth canonical model, minimum, smooth minimum model. Therefore, for algebraic surfaces, the minimum model has integral canonical volume. So only from dimension 3, you will see that in high dimensions, usually the volume is a rational number. This gives complexity for whenever we want to detect the birational geometry. So today I only concentrate on explicit aspect. So and especially after MMP, we have to use MMP. Okay, so this is one of the important invariant. So today I will talk about this canonical stability index. So since we are considering a variety of general type, so given such a variety X, so for any integer P is large enough, then you see that the canonical map, the M canonical map, which is defined by the M canonical linear system, so we usually call it phi M, or usually it's referred to as a pluricanonical map, phi M. So this is a intrinsic map defined by X. So therefore, this is usually the main source to get information from from the variety itself. Okay, so finally we have the birational invariant called Euler characteristics. This is defined from the cohomology. So this is arithmetic sum of all those birational invariants like HI of OX, or by duality, this H0 of this sheaf. We say the sheaf of holomorphic K-forms. Okay, so when V is smooth, this makes sense. But when V is not smooth, then it's still this shift still makes sense. So therefore, in general, we just call holomorphic forms. Otherwise, if it's not a complex number C, then usually in algebraic geometry it's referred to as a regular form. Okay. So today I only want to talk about some information derived from the space of this omega H0 omega V K, where K is a positive integer. So let me go on introducing these global quantities. So one is so-called Vn, another is called Rn. So given the dimension n, so you can always define these two numbers. So one is a minimal volume, so we call it Vn. So another one is Rn, that's maximal canonical stability index. So these are both some explicit numbers defined only by n. Of course, these are explicit numbers just due to some boundedness theorem proved already in birational geometry. For example, by Heiken Makana, Takayama Tsuji. Okay, so from the explicit birational geometry, the main task is to recognize these such numbers. So for example, when n is 1 or 2, these numbers are clear. For example, for smooth curves, V1. V1 is minimal volume. Is V1 is just the degree of the canonical divisor, 2G minus 2, that is 2. And R1, that is it's clear from the Riemann surface. That's R1 is 3. So genus 2 curve has the worst pluricanonical behavior. Okay. So for surfaces, this is a classical result of Bombieri. For example, as I said, V2 is 1 because any smooth surface admitting a smooth minimum model. So therefore, the canonical volume is always a positive number, positive integer. So therefore, V1 is 1. Okay, and V2 is 1, and R2 is 5. This is due to a great work of Bombieri. So we are interested in higher dimensional cases. Okay, so let me recall two classical aspects. One is today I only consider the geometry induced by the global K forms, global holomorphic K forms. So when K equals to 1, the 1 form, so it's the classical geometry. It's well known that one can define the Albanese map. So the premise is that this variety should admit a global 1 form. Okay. So on the other hand, if we consider another extremal case, that is K equals to the dimension n, then one can study so-called canonical map, provided the geometric genus is at least 2. Okay. Otherwise, we can study a pluricanonical map. Suppose that the plurigenus is at least 2. So for any given variety, one can always do in this way. So if we have no Albanese, then more or less we can study a pluricanonical map. But the premise is how can you know that the plurigenus is at least 2? But this is, as you know, this is a problem of Riemann-Roch. The Riemann-Roch formula tells you how to calculate. But in high dimensions, the Riemann-Roch is not very useful in concrete calculation, other than dimension 3 case. Okay, so so the natural question is, so how about intermediate case? For example, K between 1 and n. So two extremal cases are, so there are two maps attached to these extremal cases. So today I just talk about this question. So the condition is that suppose the given variety has many global K forms, and K is between 1 and n. So then, how is there a natural way to consider the birational geometry induced by this global K form? So this is the main purpose of this topic. So this is a joint work with my colleague, Professor Zhi Jiang, in Shanghai Center for Mathematical Science. Okay, so so here, so I start with the following observation. So this observation is very simple. So you just use some induction on the rank of the subbundle, which says given a smooth variety V, and given some torsion-free shift E on V. And suppose this shift E has global sections, that is H naught of E is positive. Then the observation says that there must be a subshift, a torsion-free subshift F, so that the determinant of F has global sections. And here is the lower bound of the H naught. H naught of determinant is larger than or equal to this ratio. Okay? So since this is a number, suppose right-hand side is positive, then this is at least 1. Okay? So otherwise, if this right-hand side is larger than 1, then that means this determinant has at least 2 independent global sections. So therefore, we can use some rational map to detect the birational geometry. So this observation is very simple, but the proof is very tricky. So it uses induction on the rank of the subbundle. Okay, so now we take this sheaf E to be the sheaf of defined by K regular K forms. Okay, so regular K forms, so set E to be omega Vk. V is a smooth variety. So the condition is that suppose this is positive. Okay, so then according to the above observation, we can find some subsheaf F. So therefore, we take H to be the determinant of F, and set L to be the determinant of the quotient. So we can consider this saturated subsheaf F so that the quotient is torsion free. So therefore, we can take the determinant of this omega Vk. So we know that the rank is combination of number A in K. Okay, so whenever we take the determinant, then we set M naught to be this number. So A minus 1, K minus 1. So that means this M naught Kx is linear equivalent to some divisor H plus another divisor L. Okay, so here some information is that H naught of capital H. Yeah, so maybe this line model has global sections. So we want to study the geometry induced by this map. So thanks to the interesting result by Campana and Pom. So the result says that here in the above relation, in this relation, the divisor L is pseudo-effective. Okay, so this is pseudo-effective. So pseudo-effective, that it's not far away from the effective divisor. So suppose you put some very small big divisor with combined with L, then it becomes an effective divisor. So whenever we want to estimate the lower bound of the canonical volume of Kx, Kv, then this H is it's almost we can consider this as a subdivisor of M naught Kx. So in the classical way, we have many. I think macho technique on studying pluricanonical maps. So suppose M naught K X has a subbundle, has a subdivisor H, which has many sections, global sections. Then it's enough for us to detect the birational geometry of this variety. So therefore. It's using our established technique. It's easy to get. It's not hard to get the following statement, which statement just says that given the number dimension n and for any k between 0 and n, and there are two constants, a n k and b n k. So they are both are positive rational numbers so that the volume has a lower bound in terms of this h naught of omega vk. So this is the dimension is also referred to as some spatial Hodge number. So usually I call it h0k. Okay, so this is something like some inequalities, like traditional inequality, Noether inequality. The traditional Noether inequality says there is a inequality between the volume and the geometric genus. So here, when k equals to n, so this is simply the usual Noether inequality. When k equals to 1, so this is a Noether type inequality. In terms of qx, that is that is so-called Savory inequality. So when k is intermediate, so that is in general we call the Noether type inequality. However, in higher dimension, it's hard. We only know the existence of ANK and BNK. It's not so explicit, except for dimension 3 case. Okay. So, for example, in dimension 3, in dimension 3, we can make this explicit. So, for example, in for 3/4 of general type, we have we know more. And here it's what we can provide. So there are such inequalities. That means the volume has a lower bound in terms of this h02. Okay, so when k equals to 2. So this is I think this is the first such inequalities. This also means that when h02 is large enough, that means then volume is large enough. Okay, so this is useful to consider the minimal volume V3. Okay, so this is useful. And on the other hand, the method also works for all dimension for k equals to 1. That means in general we have this type of Savory inequality. For any dimension, there is such an inequality that the volume has a lower bound in terms of QV or QX. Okay, so see, this works for any dimension. So I don't mention the proof of this because this is the proof of this usually. We use the induction on the dimension of the Billing varieties. Okay. So this is the first part. The first part is we just we got some inequality of the Noether type. Using this inequality in general, we have such information. Suppose that the h0k is large enough, then the volume is large enough. Okay. Okay, so now let me talk about one application to in dimension 3. So we want to know this number V3. Okay. So how do we know about V3? So so here okay. So here we have for V3 we have some application. For example, consider a variety 3-fold of general type. It can be smooth or not. Smooth or minimal, either V or X. Because what we are considering are our birational invariants. So suppose h02 is at least 4. Then using a previous argument, you see that there is subbundle F, so which has a rank between because in this case the the sheaf E is rank 3. So when h02 is at least 4, there is subsheaf F then the determinant, so we're using our observations that H naught of capital H is at least 2. Then we can study the map defined by H, which replaces a bicanonical map. So therefore, using our established, previously established result, you see that there is a very good lower bound here. That's 1/4. Suppose the H0 naught is 2, is 3. Suppose this is 3, then the subbundle, you get a divisor H. So, but you only know that either this is at least 2, or you see that the omega V2 can be either generated, almost generated everywhere, or there is a divisor H with H naught H is at least 2. So in the first case is similar to the previous case. The second case we know that P2 is positive, but then using previous inequality with Ronkai chain. So we have this inequality for any threefold. This inequality works for any threefold, and here, since P2 is positive, from this inequality, it's not hard to find that P6 is at least 2. And then using our established result, you see that the volume is, the lower bound has is 1/224. Okay. So suppose the threefold has the Q equals to Q is positive. That means suppose this threefold has one form, global one form. Then the situation is much better. So this is due to So we already have this lower bound. So this is So first So in this case, so first we have we had the first lower bound. Then recently it's the best lower bound is given by Zhijiang. So we know that the lower bound is 3/8. Okay. Suppose the geometric genus is positive, then with Ronkai, we already have the lower bound 1/75. And so suppose the Euler characteristic is smaller than or equal to 1, then we already, in 2010, we already have this lower bound. So this is sharp. Okay, so we combined everything together now. So for threefolds of general type, so the rest case is PG equals Q equals 0. Then chi OX is nothing but 1 plus the H02. Okay, so combine all what I explained. So we have the following theorem. So for threefolds of general type, suppose the Euler characteristic is neither 2 nor 3, and the H02 of X is neither 1 nor 2. And then we have the lower bound. The volume is 1/420. The equality holds if and only if the birational invariance. So this is so far the best what we can see. So in fact, so before there was an example. With this. So this is a general hypersurface in a weighted projective space. So this example has the canonical volume 1/420. And this example has the singularities exactly as here. So that is why I call B 420 here. So I should say that so far what we can do is like this. But for chi equals to 2 and 3, or H2, H0, 2 is 1 or 2. This method cannot reach. So there are some exceptional cases. We don't know how to do this for the rest cases, because in this case the 2 form are only 1 or 2. Otherwise we have everything can be done. But for higher dimensions, so far it's not reachable because we need some boundedness, effective boundedness for pluricanonical information. Okay, so but theoretically we can consider some problems when the variety has a lot of global K-forms. So that's another kind of story. So so the last part, we will talk about the so-called lifting principles for the sequence of canonical stability indices Rn. So what is the lifting property for what I mean, for what? So here I explain. So recall that I have defined N's canonical stability index, Rn. So this is a maximal canonical stability index among all n-dimensional varieties of general type. So this is a certain fixed number. Okay, so this number is important because because it's the boundary. So suppose we know R3 or R4. Well, so far R3 is between 27 and 57, as we know. But for n at least 4, so far we don't know any effective upper bound for Rn. We don't know any effective upper bounds. One only knows that Rn exists. Okay, so so here I want to extend the consideration for this in order to formulate the so-called lifting property or lifting principle. So here for any k, for example, k between 0 and 1. So we can also consider such a maximal canonical stability. That means this maximum of the canonical stability among all those varieties of dimension n of general type with the H0k is positive. Okay, so clearly for any k, this number, they are bounded by Rn. Okay, so why should I consider this such a number Rnk? This is because this is important. This is, for example, in dimension 3. This is key to know R3 and V3. So far, suppose we know for 3, for n equal to 3, suppose we know R3 2, then we can know R3 or V3. Okay, so far the main obstacle in dimension 3 is R3 2. But so I will explain So next I explain what is so-called lifting property. So this rephrases some property of the sequence Rn. So in 2024 with He Liu, this is my former PhD student who is now a postdoc in Tsinghua. So in 2024 we proved this property. That means for any given dimension n, so there is a constant so that we can lift this Rn. What do I mean Rn? So we can understand Rn by means of one dimension high varieties. Yes, that means exactly Rn equal to maximal canonical stability index among all those n plus 1 dimension varieties with a volume large enough. That means when the volume is larger than larger than this name, larger than this number, then that means all n plus 1 fold with large enough canonical volume. So then Rn is simply the maximum canonical stability index. Or in other way, we can understand this for any n plus 1 dimensional varieties of general type with a volume large enough, then the canonical stability index is no more than Rn. So there are two ways to understand. From lower dimension to high dimension, we call the lifting property. So this was proved in 2024. So here I would like to introduce some more different lifting property. All these properties are very interesting because it's useful to consider high dimension varieties, high dimension birational geometry. There are some inductive property here or lifting property here. Okay, so so another result is I recall that in 2024 we proved such a lifting property. That means for any varieties. So here you see that here we consider these are So here says this lifting property says that for any three-folds of general type with global one forms, the canonical stability index is smaller than or equal to R2. So that this shows some inductive property. That means for high dimensional varieties, if there are one form, global one form, then the birational geometry is not very bad. It's like one dimensional. For example, this we are consider three-folds. If you consider three-folds with one form, then the canonical stability index is no more than R2. That means for any three-folds of a general type with one form, then 5 canonical map is stably birational. So that means this result gives you the impression that varieties with global one form, their birational geometry is very good, not bad. So for intermediate case, we want to study similar property. So that's what I mean for lifting principle. So here is so we start with considering two forms, global two forms. So global two forms, that means H02 is large enough. So here we have the result in dimension 3 and 4. For example, when for three-folds of general type with the H02 is large enough, here this is the explicit number. When the H02 is larger than this number, then you will see the canonical stability index RSX is smaller than or equal to R1. That means there are a difference of dimension, 2 dimensions. For three-folds with very large H02, then the canonical stability index is similar to curves. So this is a very interesting phenomenon. So then we go on studying the dimension 4 case. The result is that, but it's non-explicit, but the result is that there is some constant n in n4. So when we consider all those 4 folds of general type, with H02 is large enough, then the canonical stability index is smaller than or equal to R2. So there are 2-dimension difference. Okay, so we can't help guessing whether this is true in higher dimensions. So actually, it looks very plausible. It's reasonable, quite reasonable expectation. Yeah. How about this property, lifting property for any dimension n larger than 4? So here I use a lifting property. So you from lifting, so that's R1 and R2 are lifted. So therefore, here I state with n larger than or equal to 3. If you consider the reduction, then that we can say that in dimension 3 and dimension 4 case, it's true. Then we ask dimension higher than 5, so whether this property still holds. So this is what we expected. Actually, this result we realized this 3 years ago. But recently we found that there are more properties. So that's why this year we should go on studying this problem. So we found more. So here, so here we can consider examples. So these lifting properties are actually they are sharp. So sharp in the following sense. We have 2 examples here. So it's very you can see this is trivial examples. So for 3 folds, if you take the curve, this is genus 2 curve, and you take another minimal surface S with a geometric genus as large as enough, then you take the product. You take product S cross C, then these 3 folds you just pull back the 2 forms. 2 forms, that is canonical 2 forms on surfaces. You pull back to the 3-fold. Then whenever this PG of S is large enough, then the 3-fold has more and more global 2 forms. So, but on these examples, this series of examples, you see that the canonical, it has a lot of, as many as global 2 forms. You see that the canonical stability index is exactly like the 3, because this using some inductive result, for example, for surfaces. So when the geometric genus is large enough, then 3K is birational. So you see that RSX is 3, and this 3 happens to be the R1. R1 is 3, like curves. Okay, so this means the equality holds for dimension 3. And for dimension 4, similar. You consider the products of 2 surfaces. So one is 1-2 surface. This is the worst surface. This S has 5K is birational. 4K is non-birational. So another surface is S1 is with more and more geometric genus. PGS is S1 is as large as enough. Then still, you take the product, you pull back the 2 forms on S1. Then the 4-fold has more and more global 2 forms. But on this example, you see that the canonical stability index is similar, is the same as a 1-2 surface, because there is vibration. With general fiber is a 1-2 surface. So the canonical stability, RSX is 5. And here, 5 happens to be R2. Okay, so these are trivial examples, but in high dimension we can, of course, we have such examples. It's easier. But the problem is we can't, so far for n at least 5, we can't prove this. We can't prove this. So therefore, we go on study the intermediate case. For example, the k between 1 and between larger than 1, and then so let me talk about the method. The method is the key method. The key technique is so we can use previous theorem. My joint work with He-Xu Liu. So we proved that given the dimension, so you fix the dimension, and then there is a constant, universal constant. Whenever the varieties of dimension n of general type has the volume larger than this number, then there are two cases. Either the 2k is birational, or there is a so-called Markov fibration. So what is Markov fibration? This is a fibration from the birational model W onto another variety T. T is smooth, W is smooth, and the general fiber is comes from some pair. So some pair. The pair is V and delta is proportional to a canonical divisor. Delta is equivalent to epsilon kV, and epsilon is a very, very small number in terms of the given fixed. It's a constant in terms of dimension. Okay, fixed by the dimension. Okay, so anyway, we have a fibration, and what we proved is that in this case, for two general fibers, F1 and F2, for any m at least 2, this map is surjective. That means the H naught of mkv, when we restrict to the general fibers, one is F1 and F2, so this map is surjective. That means the M canonical map can distinguish two general fibers, and when we restrict to general fibers, it's like the pluricanonical map of the fiber. That means there is a very good induction. So this tells us a very good induction. So now, when we consider the total space W, so W is birational to the given variety V, and here, suppose we have pluricanonical K-forms, holomorphic K-forms on W. Suppose we have a lot of K-forms, then it gives information on the general fiber. So we want to find some inductive property. So this is a key point. So here is the result for K between 1 and n. So in general, so the result is that there are fixed n and fixed k. So there is a constant, universal constant. Whenever the H0k is larger than this number, then we can prove that all these varieties, the canonical stability index is normal than the maximum of Rn minus k, and this number Rn minus 1, k minus 1. Okay, so this theorem works for all cases, for Rn and nk, Rn and k. So this is a lifting property, but so far it's not so satisfactory, because we don't know which one is bigger, which one is larger. So if we can compare this, then it's ideal. So, so far we found that it's at least in two cases it's sharp. For example, when k equals to n minus 1 and n minus 2, this theorem is sharp. That means we can compare these two numbers. For example, k equals to n minus 1, this is R1. R1 is 3, n minus 2, so R2 is 5. So we can very easily consider examples so that the right number is larger than the first number. So therefore, we can get, so in these two special cases, k equals to n minus 1, n minus 2, we have this lifting property. Roughly speaking, that means that given k is n minus 1 or n minus 2, there are constant m in k, so that whenever the variety has h0k is larger than this number, then the canonical stability index is nothing but, so the R in k is nothing but the maximum maximum of this stability index among all those n plus one dimensional varieties with h0k larger than this. So this is parallel to what we proved in 2024. This is the first with He Liu. Let me recall the theorem with He Liu. Okay, so so this is a theorem we proved. So this in 2024 we proved this lifting property for k equals to n. Okay, so here actually now we can extend this similar property to n minus 1 and n minus 2. Okay, so actually we can provide some examples here. We can just consider some examples. For example, here is the example. So I produce, for example, one example here. N equals to 4 and k equals to 3. So this is k equals to n minus 1 case. So we know that R32 is at least 5. So 5 is larger than R1. So therefore, from the previous theorem, we know that this is smaller than equal to R32. Okay, so here I want to produce some example which makes this equality holds. So you just take a threefold with a global 2 form so that the canonical stability index is maximal. And then you take the product with a curve of genus 2. Okay? With a curve of any, maybe, a genus GC, GC is large enough, any curve. Then this gives you more and more 3 forms. Okay? So you take one form from the curve, and you get two forms from the threefold. Then on the fourfold, you have a lot of global 3 forms. So, but for this example, you see that the equality holds. That means the lifting principle is sharp. Okay, so so finally, so the problem is for other cases with k is smaller than n minus 2. Then what happens? So this seems to be very difficult to consider, because in the intermediate case, it's hard to compare two numbers. So two numbers in this statement here. So when k is intermediate, it's hard to compare which one is larger. Suppose you can know that which is number, then which is larger, then the problem is solved. Okay, So therefore, we still concentrate on the k equals to 2 case for any dimension. So for this case, we can we want to produce this conjecture. Because we think that this is true for any dimension. So here is a conjecture AN. So here AN means fixed dimension n. N larger than or equal to 5. So then there is a constant Mn. So that for any smooth n-fold of general type with H02 larger than this number, then the canonical stability index is smaller than or equal to Rn minus 2. So this is a conjecture. And another conjecture is parallel to our dimension 3 case, that is with one form. So the conjecture, we call this conjecture Bn. So Bn means for any smooth projective n-fold of general type with one form, with global one form, then the canonical stability index is smaller than or equal to Rn minus 1. Okay, so the conjecture Bn is true when n equals to 3 or n equals to 2. Yeah. So for n larger than or equal to 4, so this is still open. Okay, but these two conjectures, they have strong relations. So I show you here. So for conjecture B, so far we have some partial result. For example, we can prove this only under the condition that the Qx is larger than n. So that means when Qx is smaller, we still can't prove this. But it's easy from our previous results. You can see that conjecture Bn minus 1 implies conjecture An. Yeah. So since we have proved B3, so therefore we can we know A4. Yeah. But so the conjecture Bn might be very difficult because so far, for example, for any fourfold of general type with Q with one form, with global one form, then the conjecture says the canonical stability index is smaller than equal to R3. But this is so far it's unreachable. Okay, so how can you see Bn minus 1 implies An? So this will this can be seen from the result here. Yeah, sorry, okay. I explained. Sorry, okay here. So this okay. Sorry. So I explained, so from here. So I have a Markov vibration. So Markov vibration, suppose the volume of, suppose W has very big two forms, very big H02. Then you see that the volume is large enough. Yeah, because we have already proved the Noether type inequality. Yeah, whenever W has a lot of two forms, then the volume is large enough. Suppose the volume is large enough, then we have this Markov vibration, and on this Markov vibration we can use the Collat's decomposition. And to see, and using semi-positivity of push forward of canonical shifts. Then you see that the fiber of the Markov vibration has one form. Yeah. Therefore, you see that using this induction, you see that the fiber, suppose fiber is one-dimensional lower, so the fiber satisfies BA minus 1. So therefore, using this surjective map, so it's easy to see that the AA holds. So this is the main strategy. So, but so far, I think this is what what we can tell about. It's still, of course, it's conjecture AN and BN are open. So we don't know how to do this further. And so for dimension 3 case, the conjecture says V3 should be 1 over 420. But so far there are still 2 cases left. So I think I stop here. Time is up. Thank you very much. Any question? Smooth or not is there? Yeah, well, I only consider 2 objects. One is a smooth model, and another one is a minimal model. So the same. Yeah. No, I don't think, because all these properties are birationally invariant. Okay, thank you.
So the next speaker today is Professor Jiwei Yoon from MIT. Professor Yoon is a leading expert in arithmetic geometry, geometric representation theory, and applications to number theory. He's had many awards, including the New Horizons in Mathematics Prize in 2018. The title of his talk is Applications of Geometric Representation Theory. Let's welcome Professor Yoon.
Thank you very much for the invitation. It's my great pleasure to give a talk here. I'm going to report on some applications of geometric representation theory to questions in algebraic geometry and arithmetic. So geometric representation theory, as the name suggests, is using geometric methods to study representations of groups, Lie algebras, etc. So here are some famous examples of geometric representation theory that are used to solve problems in group theory. For example, the Borel-Weijbot construction realizes finite dimensional representations of a compact Lie group in the cohomology of certain line bundles on the flag manifold. This is a very classical construction. Moving to finite groups of Lie type. So this is a big class of finite groups. Most of the finite simple groups are of this type. And if we want to construct and classify their representations, irreducible representations, the only known systematic construction of all representations, irreducible representations of such groups is via geometry. So this is the famous work of Deligne and Lustig in the 70s. They construct certain subvarieties of the flag variety and consider the group action on its cohomology, étale cohomology. So this is probably the first systematic use of étale cohomology in representation theory. Slightly later, in the early 80s, in the study of representations of Lie algebras, so there's the famous Kashtan-Lustig conjecture that gives a formula for the multiplicities of simple modules in standard modules, in Verma modules. And the conjecture says certain combinatorially defined polynomial actually has positive coefficients, the famous Kashtan-Lustig polynomials. And this conjecture was subsequently famously resolved by Beilinson and Bernstein on the one hand, and by Berlinski-Kashiwara independently. It's an amazing story how they connected the original purely algebraic conjecture to deep geometry of the flag manifold via D modules and the Riemann-Hilbert correspondence connecting D modules to perverse sheaves. More recently, in the past 25 years, this geometric Satake equivalence, this is a modern realization of the topic in the first bullet point, the finite dimensional representations of the compact Lie group, but a completely different realization on the cohomology or intersection cohomology of certain subvarieties of the affine Grassmannian, not of the same group G, but of its Langlands dual. And this became a pillar stone of the geometric Langlands program. So these are all well-known applications of algebraic geometry to representation theory. this talk is more about the other direction. Can we apply ideas of representation theory to prove results in algebraic geometry? So I will give 3 examples of such applications. The first one is an old story, which I actually talked about, I think 12 years ago in ICCM in Taipei. So I'll be very brief about the first application to the motivic Galois groups. Second and third applications are more recent. The second application is to the so-called Deligne-Simpson problem, is about existence of connections with a prescribed local behavior. Joint work with Konstantin Jacob. And the third application is to a purely commutative algebra problem about reducedness of function spaces on commuting varieties. It's joint work with Li Penghui and David Nadler. So I'll be brief about the first aspect. So motivic Galois group. So this is a group attached to every algebraic variety defined over Q, or more generally a motive which you can think of as a piece of cohomology of an algebraic variety. So if my variety is defined over Q, then on its étale cohomology, there's the action of the absolute Galois group of Q. So here I'm slightly more general, X is defined over number field K, but you can just think of K as Q. So this absolute Galois group will act on a étale cohomology of X. So in practice, we work with a fixed degree HI, usually the middle degree of X. That's most interesting. And it can also be a piece of the middle cohomology cut out by some group action. And motivic Galois group is simply the Zariski closure of this map, image of this map. So it's going to be an algebraic subgroup of this matrix group. This is GLN for some n, and the closure here is an algebraic subgroup. And if your X is a smooth projective, this Zariski closure is automatically a reductive group. Now, according to the classification of semi-simple or simple groups, we have classical types and exceptional types. Now, exceptional types, for example, symplectic group, you can realize there are natural examples of X such that the motivic Galois group is going to be a symplectic group, or something very close to a symplectic group. You can take an abelian variety, and typically the motivic Galois group will be the full symplectic similitude group. But for exceptional groups, it's much harder to find examples of algebraic varieties, such that Zariski closure of this map is one of these exceptional groups. And so in the 1990s, Serre raised this question whether these exceptional groups can be realized as a motivic Galois group. He specifically asked about G2 and E8. So today we know that all simple exceptional groups can actually be realized as motivic Galois group. And the varieties that it can be realized either over Q or a quadratic extension. So this is the summary of several recent developments. So first, in the G2 case, it was constructed by Detweiler and Reiter much earlier. They singled out what's called a hypergeometric motive. This is the geometric analog of hypergeometric function. So it's basically the D modules whose solutions give hypergeometric functions. And they have to carefully design parameters for the this rank 7 local system such that the monodromy group actually lies in G2 as a subgroup of GL7. This was done around 2006, something like that. During my postdoc, I realized a way to solve this problem, at least some cases, uniformly using ideas from geometric Langlands program. And with that, I solved the case of E7 and E8. So G2 actually is also kind of reconstructed. And with the modification, this method also works for F4. So I'll say a bit more about my method. And more recently, the E6 case, that's the only case left out, was solved by these authors by a more number theoretic approach using modularity lifting techniques. Okay, so the idea of the construction is to construct a local system on P1 minus 3 points that comes from geometry. So this looks like an even harder problem than the original question asked by Serre, because now instead of constructing a single variety, I need to construct a family of varieties, a one-parameter family. But the examples we're looking for is not a random example. It has the so-called rigidity property. This means this local system does not have infinitesimal deformations. So this is like isolated points once you fix its local monodromy around 0, 1, and infinity. So these once the local system is rigid, it is believed that they should all be motivic. They should come from geometry. This was a conjecture of Simpson. So we set out to construct such local system. Once we have it, we can pick a Q point on P1. That fiber will give us motivic Galois representation. But the key idea here is to not to construct the local system directly, but to look for its counterpart on the other side of the Langlands correspondence, namely an automorphic form on G dual. So this is where geometric representation theory came in. So yeah, this is as much as I want to say about the first application. Just very briefly, that the new idea here is to start with the other side of the Langlands correspondence, and what it produces is something is a local system, is something that people, algebraic geometers care about. Okay, so more recent application, the Lin-Simpson problem. So classically, the Lin-Simpson problem asks for to find local systems on a punctured Riemann surface. So let's start with a reductive group G, complex reductive group. X is a compact Riemann surface, and then we puncture a few points, finitely many points. Suppose we're given a conjugacy class in G, one for each point you puncture, and we want to look for a local G local system. So this means homomorphism from the fundamental group of this punctured Riemann surface to G, such that its local monodromy, so the loop around each puncture, will map to an element in the given conjugacy class. Okay, so yeah, so this is finding group theoretically. It's just finding a homomorphism such that prescribed generators in this free group will map to prescribed conjugacy classes. And you can make it into a completely algebraic problem, just solving this matrix equation. the fundamental group of this punctured Riemann surface can be presented in the following way. So we have the AI, BI generators. These are loops on the compact surface, and then product of the commutators is the product of local loops around punctures. Now we are looking for solutions of this equation inside G. And moreover, we want these Gx to be in the given conjugacy classes. Okay. So solving this, if G is GLN, we are really looking for a bunch of matrices satisfying this equation. It's not hard to come up with examples where this equation does not have solution. So it's actually a subtle question whether you can solve it in GLN. So this Betti form of the Lin-Simpson problem, there has been a lot of work, and I just list some main contributors: Simpson, Kostov, Crowley-Bovey, and many more. It's related to representation theory of quivers, pre-projective algebras, etc. So what we're looking at is a variant of this problem where we replace local systems by connections. So this is called a de Rham form. So we still work over the same punctured Riemann surface, but now we are looking for a principal G bundle with a connection. Okay, so this is E is a principal G bundle. The connection locally looks like D plus a connection form. It's a Lie algebra valued one form. Because we work over punctured X, this form is allowed to have poles around each puncture. Now, instead of fixing local monodromy, we fix the isomorphism type of the connection on the formal neighborhood of each puncture. So given a local connection on the formal puncture disk, so this is going to be one form, but is basically a formal power series, formal Laurent series with coefficients in the Lie algebra of G. Given such, we are looking for a G connection such that on each puncture disk, X in this finitely many points S, it is gauge equivalent to the given local connection. This is the Rham or additive form of the Lin-Simpson problem. But it's actually more general than the original Lin-Simpson problem, because Betti form, the local systems correspond only to part of the connections, namely the connections with the regular singularities. And here we are more interested in beyond that case. What if the local connections have irregular singularities? So what we can solve is a specific case. G is any reductive group, but the curve is P1, and we only have two punctures, 0 and infinity. At 0, it has a regular singularity. We fix one matrix, one element in the Lie algebra, capital A, and the connection has only a simple pole at t equals 0. So A times dt over t is the polar part. And the rest of ... these are all, this is a power series in T, no poles. At infinity, we allow irregular singularity. So by the general theory of classification of irregular connections on a formal punctured disk, every connection can be written in this form. So, sorry, I did something. Okay, at first you can ignore this fractional powers of the local parameter. So this tau is just T inverse, local coordinate at infinity. let's pretend this small m is just 1. So we're just having the polar part, tau to some power in the denominator. And in the numerator, these elements are all in the same Cartan subalgebra of G. So the point here is all the polar parts can be simultaneously diagonalized. If G is GLN, I can arrange that all these terms are diagonal matrices simultaneously. This is the part that's strictly, the polar degree is strictly bigger than 1. So beyond the simple pole part, they can be simultaneously diagonalized. That's the main content of this local structure theory. In general, we won't be able to do this without taking a root of the local parameter. So you can pass to a cyclic covering of the original formal disk. Then you can put your connection into this diagonal form. Now, this is the general theory. Any local connection can be put in this form. But here we consider a specific case. We put an open condition on the leading term. We ask that the leading term is regular semi-simple, so in the Cartan. So namely, it's not annihilated by any root of the group. So for GLN, this means the first diagonal matrix, all the diagonal entries are distinct. So this is the specific condition we impose on this local behavior at infinity. So now we are going to fix this nabla 0 and the nabla infinity, which is the same as fixing this matrix A and fixing this polar part. All these numerators, they are all in some Cartan subalgebra of G. This is the given data. And then we are looking for a global connection on P1 whose local behavior at 0 and infinity are as prescribed. What's really important here are these two numerical data. One is the slope, d over m. So if we go to the previous slide, this is just the leading, the largest polar part here. So it's a fractional power of the local parameter, d over m. And the invariant at 0 is, of course, the residue. That's the element matrix A in the algebra. So the result is an explicit solution of the Deligne-Simpson problem for this in this specific situation. So if I'm given this nabla 0 and nabla infinity, as in the previous slide, I can give you an algorithm to decide whether there's a global connection with these local types. Explicit means, it doesn't mean that we give an explicit construction of this connection. It means we give an explicit yes or no answer in terms of these two invariants, the slope and this residue at 0, its adjoint orbit. Okay, so that's the, so let's look at an example. This example was actually due to previous work by these authors, 5 authors in 2022, and we were inspired by their result, although the method was completely different, but they were the first to look at this type of question. And they solved the GLN, the SLN case. It has a very simple, nice answer. If the slope at infinity is this fraction, d over n, and the residue at 0 is lies in some nilpotent orbit, then the Deligne-Simpson problem for this specific type has a solution if and only if you look at the Jordan normal form of this nilpotent matrix, it's a partition of n. And for partitions, we have a natural partial order by summing up the first I terms. So this partial sum gives a partial order. And the Lin-Simpson problem has a solution if and only if this nilpotent orbit is in this partial order is bigger than or equal to the most balanced partition of n with d parts. So d enters here. D is the denominator of the slope at infinity. Most balanced means these d parts are either equal, at the most they differ by 1. Okay. So it's a very explicit criterion for the existence of the global connection. And for other groups, so the solution is of this flavor. I'll give some special cases. If G is, for G is anything but this slope at infinity is 1 over the Coxeter number, this is the smallest positive slope you can get for G connections. Then this nilpotent orbit, this is the adjoint orbit of the residue at 0. Now we are not assuming it's nilpotent anymore. But in this case, the Lin-Simpson problem has a solution if and only if this adjoint orbit is a regular orbit. Namely, its centralizer dimension is the rank of G. It has the adjoint orbit has the biggest dimension among all adjoint orbits. This is the one extreme case where the irregularity at infinity is as small as possible. At the other extreme, if the irregularity at infinity is at least 1, then there's no constraint on the residue at 0. The O can be any adjoint orbit. Now, in between, the answer is formulated in terms of representations of Weil group and representations of double affine Hecker algebras. So these are much studied objects in representation theory. A lot of the invariance here can be calculated effectively, and our answer is given in terms of these effectively calculable quantities. Okay, so that's the statement. Now, what's the idea to prove such a statement? So we look at several moduli spaces closely related to moduli space of connections. So most relevant is the moduli space of connections itself. So you can form this moduli space, G connections, satisfying the given local conditions at 0 and infinity. It naturally forms a moduli problem. And this space turns out to have good properties. For example, it's smooth. Now, the next, as taught to us by Simpson, we should consider one parameter degeneration of the Ron moduli space to the so-called Dobol moduli space. So the notion of a connection is a bundle with a D plus a 1 form. That's the connection form. Now, if you ignore the D in the front, if just a bundle plus a 1 form, that's the notion of a Higgs bundle. So Dobol moduli space is the moduli space of Higgs bundles. And we can impose similar local conditions. So this polar part of the Higgs bundles at 0 and infinity, we can just copy what we had for connections. And these two moduli spaces sit inside a one-parameter family. So this one-parameter family really has a scaling symmetry. All the non-zero fibers are all isomorphic to the Ron moduli space, and the 0 fiber is isomorphic to this Dobol moduli space. Okay. And further, this scaling symmetry contracts everything not just to arbitrary points in this 0 fiber, but to a much smaller subvariety in this double moduli space, which has half dimension inside it. It's called the central Hitchin fiber. So Hitchin constructed an integrable system on this double moduli space called a Hitchin map. It's a Lagrangian fibration of this symplectic manifold. In our situation, we designed these local conditions such that this Hitchin moduli space has a scaling symmetry, and the Hitchin base contracts to a single point. And the fiber over that point is what we call the central Hitchin fiber. The central Hitchin fiber is thanks to the work of Bao-Chao Guo in his proof of the fundamental lemma. There's a general pattern here that relates Hitchin fibers to affine Springer fibers, which is a subvariety in the affine flag manifold. So we designed a situation such that the central Hitchin fiber is homeomorphic to an affine Springer fiber, defined by some element in the loop Lie algebra. And this loop Lie algebra is essentially the polar part of the connection form at infinity. Okay. So this is a specific Hitchin moduli space that was studied in my joint work with Bezrukamnikov, Pablo Borghida Alvarez, and Michael McBreen. And then the existence of global G connections, thanks to this scaling action. So the Lin-Simpson problem is really asking whether our moduli space is empty or not. Okay, so it looks like a very naive question to ask for such a complicated algebraic variety. But if it has a point, this scaling action will take that point to the central fiber, to the central Hitchin fiber. And the question becomes whether there exists a certain point in the Hitchin fiber, or rather in the affine Springer fiber, satisfying certain conditions that encodes the residue at 0. So this adjoint orbit will be a further condition for the point on the affine Springer fiber that you're looking for. It's called a reduction type. So we reduced the problem to finding a specific point on the affine Springer fiber. And this question was related to my previous work with Alexei Oblonkov on the geometrical representation theory of rational Schrödinger algebras, and on my and also related to my work on the Kashtan-Lustig map. So this was once we reduced to this question on affine Springer fibers, we have existing tools to solve it. So this whole idea basically uses this ideas from non-abelian Hodge theory. Okay, the third application is to a question in commutative algebra. It's about commuting schemes. So again, we start with a reductive group, complex reductive group. And we consider pairs of commuting elements in this group. Okay? So this is naturally an affine scheme. For example, if G is GLN, we are just looking at pairs of matrices such that when I write down the matrix entries of G1 times G2 versus G2 times G1, I just impose that entry by entry, these two matrices are equal. So it's defined by two n square variables and n square quadratic equations. And G acts on such pairs by conjugation. There's a folklore conjecture that says this commuting scheme should be reduced. Okay, so such question in commutative algebra is usually subtle, and so the reducedness is not something you can detect by topological methods like cohomology, Betti cohomology. Yeah, so this is a long-standing conjecture, and even the GLN case is open. And we also can't solve this conjecture. This is an example for GLN. We solved something much weaker, much less ambitious, but was still open. We look at only the G invariant functions on the commuting scheme. Okay, so those functions that are invariant under the conjugation action by G, simultaneously acting on both elements in the commuting pair. So the toy model of this question is, instead of two elements, we just look at one element. Then we go back to this classical theorem of Chevalier that says for a Lie group or for a complex reductive group, if you look at conjugation invariant regular functions, then all such functions you don't lose information when you restrict it to a maximal torus. And you exactly get Weil group invariant regular functions on the maximal torus. Okay, so for example, all the characters of algebraic representation of G can be written as characters on T that are Weil invariant on the Weil group. And so that's Weil character formula is expressed in this form. Okay. So the hope here is when we go to a pair of commuting elements, we can say much more about this ring of invariant functions. So we have no idea how to attack reducedness of this ring directly, but maybe we can try to solve a harder question by completely determining the structure of this ring and just read from it that it's reduced. And the Chevalier restriction theorem gives us a prototype. So for GLN, this is just saying we get symmetric functions in variables. So indeed, our result is very similar to Chevalier restriction theorem in two variables. So if we restrict the pair of commuting elements to only those elements that come from the same maximal torus. Okay, so T times T, of course, any two elements commute there. So that's a very small part of the commuting scheme. Any conjugation invariant function will restrict to a function on T times T, and automatically the function will be diagonally invariant under the Weil group action. This turns out to be almost an isomorphism. So that's what we proved. So for this to be literally an isomorphism, you need to impose that G is, the precise condition is the derived group of G is simply connected. Okay, but you can just take G to be SLN, and this is true. Okay, so this is one special case of our result. This result was also, there's a lot of previous work on this, towards this result. People already proved that up to reducedness, the left-hand side, if you take the reduced ring, it is the right-hand side. Okay, again, the reducedness is the new claim here. So for GLN, we get these diagonal symmetric functions. What happens if G is not simply connected? So this is a very interesting, very interesting phenomenon happens. You can already see it in PGL2. So in PGL2, there are this pair of elements, diagonal 1 minus 1, and this Weil element, anti-diagonal 1, 1. If we compute their commutator, if we compute the product inside GL2, you will find that they don't commute. Okay, if you this will just switch the two diagonal elements. If you conjugate G1 by G2, you get -1 and 1. But if you pass to PGL2, it becomes the same. So they commute in PGL2, they don't commute in GL2. Okay, so this is the interesting phenomenon when your group is not simply connected, you have more commuting pair of elements than in the simply connected cover. And what's subtle here is that this pair of elements cannot be simultaneously diagonalized. And if they don't simultaneously diagonalize, we certainly miss them when we restrict to t times t. So in the statement of the first theorem, we only restrict to those elements that come from the same torus, and we miss this example. So, so this suggests how the theorem fails for PGL2. And indeed, in this case, this example, this pair of elements is up to conjugacy, is the only pair of elements that we miss by restricting to t times t. In general, for a semi-simple group, this commuting scheme has many connected components. And the components are exactly indexed by the fundamental group of G. So for G simply connected, of course, fundamental group is trivial, and we only see one component. And for PGL2, we see two components. And this lies in the smaller component, which has only one, essentially one such pair up to conjugacy. So the more general form of our result describes regular functions on every component, so the statement is a little more complicated. I'm going to ignore it here. We also prove variance if we replace the group by the Lie algebra. For example, you can consider commuting pairs of one element from the group, the other element from the Lie algebra, or just both elements are from the Lie algebra. And we prove similar results. Here, you don't need to worry about the subtlety in PGL2. For any reductive group, restricting to the obvious analogs of t times t will give you isomorphisms of invariant functions. So all these results were previously known up to reducedness. Okay. We also prove a derived version of these results. So let's look at, let's do a simple dimension count for even for GLN. So we mentioned that for G equals GLN, this equation involves two n square variables and n square equations. So naive count of dimension would give you n square. So commuting pairs of elements should form an n square dimensional algebraic variety. But the actual dimension of the commuting variety is larger. It's n square. So in the case of GLN, it's n square plus n. So you can just look at those elements that are simultaneously diagonalized, and you can easily convince yourself the dimension is at least this much. That means among the n square equations that we impose, there are redundancies. And in algebraic geometry, these redundant equations, we don't just simply throw them away. We want to encode them into the definition of this variety and upgrade the algebraic variety to what's called a derived scheme. In this case, this is a concrete object. Because everything is affine, we simply look at its ring of functions. Now, instead of previously, we have these two n square variables, and then we impose n square equations, which amounts to tensoring over OG with the augmentation, with the some specific homomorphism to C corresponding to the identity element. Instead of taking the usual tensor product, we take the derived tensor product. So the result will be differential graded algebra. So our theorem actually describes this differential graded algebra in complete generality. Again, here I only state the simply connected case. So if you restrict to, again, those elements that are simultaneously diagonalized, the derived version will have an extra term here. This lives in the negative degrees. So it's the exterior algebra in the dually algebra of this T. So this encodes all the redundant equations that you impose. Because if you look at a pair of elements from T times T, of course they all commute. You can still artificially impose the equation that G1 times G2 equals G2 times G1, but all such equations are redundant. And this T star is exactly quantifying those redundant equations. So already on T times T, you see those redundancies. And our theorem says, again, you don't lose any information even when you want to study this derived scheme by passing to simultaneously diagonalized elements. And then you just impose the simultaneous Weil group invariance. This precise result in the derived case was conjectured by these authors previously. Okay, now the idea of proof. Again, it's a very roundabout proof. Well, I should say in all these applications, none of these applications in the beginning was a targeted application. So we didn't want to solve the Lin-Simpson problem. We didn't want to answer Sayre's question before we actually realized we already answered the question. So we were just studying what I think are fundamental objects in geometrical representation theory, and as a pleasant surprise, they lead to nice applications. So also in this case, it was we were motivated by natural questions in the geometrical elements program, and it led to such applications. So to relate commuting scheme with geometrical elements, we recall that a general a general place that commuting schemes show up is when you look at local system on the torus. A torus fundamental group is a pair of commuting elements. This is the free abelian group of rank 2. So if you look at local systems, G local systems, it's the same as a pair of commuting elements in G. You can even make this very precisely on the level of moduli spaces. The moduli space, even a derived moduli space of G local systems on a 2 torus is exactly this commuting scheme, the derived version, modulo simultaneous conjugation as a stack. And the ring we want to study is exactly the global regular functions on the right-hand side. But the left-hand side is the main player in geometrical elements program. So the idea here, again, just as in the first application, we do something on the automorphic side and conclude something on the spectral side. Here, again, we want to understand global functions on the on the moduli space of local systems on the torus. But the way we do it is to find a matching object in the automorphic side. So what is the matching object? Global functions is the endomorphism ring of the structure sheaf on this algebraic variety. So O, structure sheaf. So geometrical equivalence tells us there's an equivalence of categories between coherent sheaves on this moduli space and constructible sheaves on some other moduli space. So our strategy is to find this other object corresponding to the structure sheaf here and calculate its endomorphism ring. And hoping that that calculation can be made more explicit. So let me briefly review the relevant version of geometrical equivalence. This was the Betti geometrical equivalence proposed by Benzvi and Nadler. So the statement is this equivalence of categories. The left-hand side is what's called the automorphic side. It involves the moduli space of principal G-check bundles. So here G-check is the Langlands dual of G on this compact Riemann surface, now viewed as an algebraic curve. So this is an algebraic stack, and we look at constructible sheaves. Well, technically they are not really constructible. We allow infinite dimensional stalks with a very important condition of having singular support, some prescribed singular support, which constrains where the sheaf can jump. On the other side, what's called the spectral side, this moduli space of local systems, G local system on the same Riemann surface. So this moduli space only depends on the fundamental group of X. This is a purely topological invariant of this Riemann surface. And we look at some version of coherent sheaves. Okay? So this conjecture, of course, there's a big discrepancy of both sides. The right-hand side is a topological invariant of X, and the left-hand side apparently depends on the algebraic or conformal structure on this Riemann surface. So this doesn't look very plausible at first sight, but it turns out to be true, and it's highly non-trivial. It's still an interesting open question to prove directly that the left-hand side is a topological invariant of the Riemann surface. So this is now a theorem. This is a consequence of the recent amazing breakthrough by a big team led by Dennis Gaisgray and Sam Raskin, including Chen Lin from Tsinghua. They prove the original version, so-called Duram version of geometrical equivalence conjecture, and this Betti version is actually a consequence of the Duram version, although that implication is also non-trivial. So this is already known. But at the time of our work with Li Penghui and David Nadler, this was not known. So we had to prove a fair amount of genus 1 Betti geometrical equivalence to get our application. So in the genus 1 case, so as I said, the strategy is to find a counterpart of the structure sheaf on the spectral side, this O, and calculate it on the automorphic side. So this counterpart is called the Whittaker object. This is the analog of the first Whittaker coefficient in the classical story of automorphic forms. And the matching of these two objects is, again, a folklore in geometrical equivalence program. In the final proof of the geometrical equivalence, this is a sort of a first input in the final proof. So our task becomes computing the endomorphism ring of this Whittaker object as a constructible sheaf on the moduli space of G check bundles on X. Of course, this is only useful if we can say non-trivial things about this Whittaker object. So indeed, we can study the geometry of this Whittaker object fairly explicitly. So we need to prove part of geometrical elements in genus 1 to identify this Whittaker object. So fortunately, what it involves is only what's called a semi-stable part of the moduli space of all G-check bundles. And this, on the genus 1 curve, the semi-stable G-check bundles, this part is much better understood. And we describe this Whittaker sheaf in terms of Springer theory. And finally, this allows us to compute its endomorphism ring. So this is morally the strategy, but if you look at our paper, we actually never mention genus 1 curves. We use an equivalent model for moduli space of G-check bundles on genus 1 curve, known as the cocenter of the affine Hecker category. So it's a purely local model, but it serves the same purpose. So some recent work in progress of the same authors, we want to give a direct geometric proof of Betti geometrical elements in genus 1. So the proof by Gaitscory and collaborators uses a lot of representation theoretic tools, including affine Kasumuri algebras. At least in genus 1 case, we believe there is a much more direct geometric proof, which is an extension of our previous work that I mentioned. We prove some part of it in order to get this application. Now we are working on completing that into geometric proof in genus 1. And the idea, this is an idea that I explored previously with David Nadler, is to study how the spectral side changes as your algebraic curve degenerates, in general from a smooth curve to a nodal curve. In this case, from an elliptic curve to a nodal rational curve. So this is kind of once you degenerate to a nodal rational curve, this category is much better understood, and you want to use it to use the sort of known examples to study new examples. So that's a general strategy. That's the end of my talk, but I hope it's not the end of application of geometric representation theory. Thank you very much.
Thank you so much for the great talk. Any questions for Professor Yoon?
I have a question. Okay. Could you turn to the page about the idea of the proof of the second program, the Simpson program? Okay. Yeah. About the fourth point. Okay. So you mentioned one direction is clear. If you know the existence of the solution of the Simpson problem, then that means then you get existence of point of M gamma.
Yes.
So my question is about the inverse as a converse. Why the existence of points in M gamma implies the existence of the collection?
I see. Yeah, that's a kind of a deep question at a technical level. So basically, we prove nice geometric properties about this one-parameter family. Like it's actually smooth over A1. It's not just if you can have if the family is not flat, certainly you can have points in the central fiber that don't come from general fiber.
Right.
Once it's flat, then then every point has to be the limit of some point from general fiber. Yeah.
And also, I wonder whether there is a arithmetic version, okay, of this the Lin-Simpson program. So let me put it this way. Suppose K is just the algebraic closure of the finite field, and we consider the Laurent series,
Yeah.
Homo-Laurent series.
Yeah.
Okay, that is KT. Suppose we give a representation of the Galois group of this field. Is it possible to L-adic representation? Okay, is it possible to find a global L-adic Galois representation of the function field of the finite field over finite field? Okay, that is it possible to find a local system, L-adic local system on P1 minus 0 and infinity, so that its monodromy at infinity is given by the one that I just mentioned, and its monodromy at 0 is 10.
Yeah, so yeah, that's certainly a natural counterpart of this question. So the answer, even in the situation analogous to this specific thing, has to be subtle, because our answer is I gave some examples of the answer. The general answer is in terms of combinatorics of Weil groups and double affine Hecke algebra. But here's the general strategy to attack this problem. So again, we start by designing an automorphic situation. So turn the local monodromy of your Galois representation into level structures on the automorphic side, and try to come up with automorphic forms with those specific level structure. And then once we know, then we can use Vincent-Laforgue's result to get Galois representations of your automorphic form. But now one needs to check that the local monodromy does indeed give you back the local monodromy you started with. So you need the local global compatibility in function field long lengths. This is not known in full generality, but I can believe in 5 years experts at least should have made enough progress to solve many such questions.
And also, in your program, in your formulation of the program, you don't need the Stokes structure, Stokes phenomenon, for the monodromy at infinity. I mean, for this program. You don't need that?
So it's not in the, for this problem, we don't need to consider Stokes structures, but naturally companion of these moduli spaces is the Betti moduli space, which is essentially the moduli space of Stokes data. And that, so there's a drum, there's the Debol, there's Betti. All those spaces were studied in my paper with Bezrukamnikov, Borghede, Alvarez, and McBreen. We consider all of them and prove geometric results about them. It's certainly part of the story, but for this application, we don't need to mention it.
Okay, thank you so much. I think that's all the time we've got for questions now. But yeah, feel free to ask during the break. Yeah, so we reconvene at 11 for the last talk of the morning. Thank you again. not like that. Sorry. What? Turn them out. You're using the screen or not?
I do. How do you use the box?
So no screen at all.
No screen.
Yeah, so probably they should be turned out. Yeah. Okay, thanks. All right, so the final speaker of today's morning session is Professor Yaping Yang from the University of Melbourne. She is a leading expert in geometric representation theory and quantum groups. She will be talking about line operators, cohomological whole algebras, and affine Grassmannian today. Thank you so much. Let's welcome her.
this class, the category 1 is unknown. Category 1 operator is the progress coherent sheets on this REN, which is the modular obstacles. So the modular obstacles construct the Fn. the focus on the case when the n is trivial. And so for the non-trivial n, so there are some examples computed by collaborators. And so for that construction, so mathematically, what I can say is, so first of all, the quiver with potential always have an extra dm action, extra c star action. So this has a natural quantization. So natural quantization. Compared to the digital Mathematicians. And also our construction work with lattice in general with that case. All right, so any questions?
Can you go beyond cotangent type in your construction?
So what?
Can you go beyond cotangent type?
Cotangent type, so maybe we can talk more. So I'll give you the construction. So I'm not sure how to translate it to this M. Okay, so the part 2 is the construction. And so input the string, so I call it a Flavia datum. And so I have to warn you, I'm responsible for this notion Flavia datum, and I'm still yet to convince my collaborators this is the right input. And so this thing is, of course, motivated by the notion of group datum of listed. You can find this notion in listed groups. Okay. So I have three things. So I start with a quiver with potential, where here is a quiver consists of set of vertices, set of arrows.
The micro is not on.
What's that?
The microphone is not working. We are aware, and it has been. So can you fix it or not?
So what? Maybe I didn't see it on.
Oh, you didn't turn it.
Oh, sorry.
It's working.
Now it's working.
Yeah.
Okay. Yeah, that's fine. So the mathematical part starts now. Right. So the first part is a quiver with potential. I got a quiver, set of vertices, and set of arrows. So just draw a nice quiver is a directed graph. Maybe I draw it this way. So that's a quiver. And so the potential means that I got a linear combination of cyclic paths in this path algebra CQ. Okay. And so second part, I need two finitely generated abelian groups. One, I call it x lower star. One, call it x upper star. So if you see the language of line operators, so those two lattices has to do with electric or magnetic lattices. Okay, and so those things has a perfect pairing between them, x lower star and x upper star to C. Okay, so for the compatibility between 1 and 2, so I wanna, so there are maps from the set of vertices to the two lattices. So maybe I call this F. Oh, I can hear myself louder. Maybe let me check. Oh, I see. Okay, I can shout. Okay, so there are two maps. One is F and one is G. I to X lower star, I to X upper star. In Lustig case, those are two embeddings, such that so if I look at the pairing, Fi G of J, so this pairing has to do with number of arrows. Of my quiver. Okay. Right, and for simplicity, so I can have a simple model. So today, so you can think this X lower star has a basis, so you call it I, and the X upper star has a basis, I call it I prime. So those are the dual bases. Okay. And so if this is if this Calabi-Yau datum is not natural for you, so you can also start with a framed quiver with potential. So for such data, I can associate with a framed quiver with potential, Q frame and W frame. So that's a framed quiver with potential. Okay, so let me give you an example. So for instance, if I start with a dinking quiver of G, so this guy has a dinking quiver, let's say type A3. And so that's my Q. Oh, sorry, that's not my Q yet. So so this Q framed, so the usual convention is I double the quiver, and so adding the edge loops. So those gauge vertices corresponds to this I, and I can have another copy I prime. So those are the framing vertices, has to do with the dual basis of X upper star, so going up and down. And so you usually see this picture in the Nakajima quiver variety. Okay. All right, and so the frame the potential, so you can take, so I have this L for the self loop, and I have HH star, and I have arrows going up, arrows going down. So this L of HH star plus IJ. So if you get rid of those self loop, that's a moment map of the representation of framed quiver. Okay, so that's an example of framed quiver with framed potential. And now, so let me okay, so let me tell you briefly what's the role of those two lattices. Okay, so I can fix the dimension vector V rising X lower star positive, and which means it is colored by the vertices of the quiver. So I look at this Hilbert scheme, lower star, which is direct sum over, which is disjoint union over all the dimension vectors, and A to the V. So this is a symmetric power of A. So that's a moduli space. So this is a moduli space parameterizing the I-colored points on the curve A1. Okay, and similarly for the so that's corresponding to one lattice, and for the other, I have X Hilbert upper star as well. So the Hilbert will be Hilbert lower star cross Hilbert upper star. Okay, and so this guy is a commutative monoid. Means so if I have two sets of points, I can take a union. So the union from Hilbert cross Hilbert to Hilbert. So that's a monoid structure. So this is by taking union of points. Okay, and so this tells you if you look at the coherent shifts on the Hilbert scheme, this has a Euro convolution tensor. Okay, so the convolution, if I have a sheaf and I have another sheaf, I can do the box of two sheaves, then use this union push forward. So that's a Euro convolution on the coherent sheaves. Okay, it's my time. Okay, so easy lemma. So those convolution product can be twisted. If I have a bi-extension line bundle L, okay, so on the product of Hilbert schemes. And so we can use this line bundle to twist the convolution, gives L twisted convolution. Okay, so this means the following. So I have a sheaf. If I twist L of G, so that's F box G, and tensor this L, then push forward. Okay, so that's the row of the two lattices that give me a parameter space Hilbert scheme. Okay, so now the row of the framed quiver with framed potential. So for the original quiver with potential, the quiver consists of only gauge vertices. So I can consider the critical coha. So the critical cohomological Hall algebra. So this is introduced by Kontsevich and Sobman. And so nowadays, this critical coha is also called 3D coha because it has to do with shifts on 3 Calabi-Yau category. So that's the same thing. And so this coha, by definitions, are denoted by H. So H is, I take the critical cohomology, so compact supported cohomology of the modular of representations of my quiver up to the change of basis GLV action. So this is the modular of representation of the quiver. And so the coefficient is given by trace of W. So this is a sheaf So this guy is a sheaf of vanishing cycle associated to the function trace of W. Okay, so it's a constructible sheaf. And so normally we take the dual of this vector space. Right, so this is the critical cohomology in Andrei Okhenkov's talk. And direct sum over V's. Okay. I take the, so for a curve, if you have a number n, so this is the a to the n quotient by Sn, because the curve is the same as the Hilbert given n point on a curve. Yeah, it's a curve. For surface, of course, it's different. Yeah, for surface, you have to be careful. That's right. Yeah, I think different people use different convention. I heard lots of maybe Gatsby call it configuration space, but it's the same thing. Okay, so I get this Koha. Right. So this is associative algebra constructed by conservative Soberman using Hall multiplication, and right. So you can also think this is a categorical version of dt, because you take the generating series of that thing, you get the dt series. Okay. So I get an algebra from the quiver with potential. Now if I add in framing, if I have this, and I can look at the moduli space. So I just denote MVW. So this is the representation of the framed quiver with dimension vector VW up to GLV action. And here I add in the cyclic stability condition. Okay. And the resulting modular spaces still have a symmetry GLW and extra C star. Okay, so for example, Nakajima quiver variety arrives this way. Okay, so that's the familiar objects. And now so I want to pack things differently. So I'm going to fix L, which is a positive number. So I'm going to call this level. And so I'll fix a lambda, which lies in x star positive. And I call this co-weight. So I fix a level, fix a co-weight. And I look at all the dimension vector W, which is L times lambda. So lambda multiple of this co-weight lambda. And so I'm going to choose a nilpotent element gamma, which look like this. So it's an element in GL of W. And I want it's a nilpotent element. So it's a principal nilpotent element of size L, and there are lambda blocks of them. Okay, so I'm going to choose this particular nilpotent element, gamma. And so this gamma will introduce a function on my moduli. And so the function is defined by pairing with the moment mark. At the framing vertex. Okay. Right, so there are some function on the modular space. Okay, so for this modular space, I'm also taking the critical cohomology. So I have compact supported cohomology of the equivariance of this modular space MVW. And so this perverse sheaf, I have contributions from the framed potential W frame, and I also have contributions from this nilpotent element I'm taking. So I'll write gamma there. Okay, so this guy. And my W is special, so it's L times lambda. And I take all the possible dimension vector V's. Okay, so this is roughly speaking the critical cohomology of the modular space. And for the shorthand notation, I'll denote this by dp h bar of L lambda. So it depends on the level, depends on the co-weight, because there's a C star in the equivariance, so there's a natural H bar there. And so this dp has to do with compactification. So D stands for Drinfeld, P stands for Plucker. So I'm going to use this shorthand notation. Okay, so it's an object in the coherent sheaves on the Hilbert scheme. And maybe I still need to add an extra parameter space come from the H bar. Okay. Huh? Dual. Thank you. Okay, so that's quite a long preparation. And theorem A. So first part is critical cohomology of this modular space. So dp h bar L lambda. So this guy is a module over the coha. So that's a 3D coha of Conservich-Solomon. And this is true for any level and weights. Right, so in other words, I take the original quiver potential, I get an algebra, and I look at the different modular space, I get a module for the coha. And part 2, so assume the framed quiver is symmetric. So this condition can be relaxed by the recent work of COZZ, Yalong Cao, Andrei Okenkov, Zhou Zijun, Zhou Yehao. So for simplicity, I'll just assume the framed quiver being symmetric. So this condition is to guarantee there's a stable envelope class, stable envelope exists. Okay. Right. So so if I fix my co-weight lambda and vary this level L, and so the claim is there exists an algebra structure on this dp thing. For different L's. Sorry, why what? It's so the I didn't tell you. So yeah, let me see. So so I didn't tell you this equivariance. So this part comes from the fact that so there's a GLV. So acting on the representation of this framed quiver VW. So this GLV will, right, so in particular, if I do this representation, yeah, so it comes from this, so come from GLV of a point. So everything will be modules over this guy. And this guy, so that's functions on A of V. So if you write down spec of this cohomology with respect to GLV, so you get this symmetric power AV. Right? So that's where it comes from. And so remember I have this Hilbert lower star, Hilbert upper star. So this guy comes from the gauge GLV action, and this comes from the framing GLW action, something like that. Yeah. Right. So the extra H bar is, so in the quiver variety case, so everything is symplectic, so you can scale the arrows to get the H bar. And for the 3 Calabi-Yau category in general, so you just have to make your H bar action, C-star action, so that the potential is invariant. Yeah. I probably simplified in my talk, and there is a case if you have if your quiver is empty, but you still have those 2 lattices. Yeah, so that's some example we are also interested in, and it turns out it has to do with the Afan-Grass mania of the torus instead of a reductive group. It's not, I think for general potential, you just have to assume the potential is invariant.
But what's the action? Is scaling the arrows?
Yeah, scaling the arrows, yeah. And, right, so in some cases, there's a nice choice. Like type A1, I think we make things so that it's compatible with this cluster algebra people's convention. But for the definition, of course, you just need so that the potential is invariant. Okay, right, so let me say something about the algebra structure. So I have dp L1 lambda, and so there's a theta, so I'll say something about that. L2 lambda, so it's a graded algebra structure, L lambda. L is L1 plus L2, where, so this algebra structure construction relies on the stable envelope. So this multiplication is given by the stable envelope. So in the quiver variety case, we just need to use the construction in Molliger-Konkoff and in general COZZ. And so there's a theta here. So this is a by extension line bundle. And you can read off from the stable envelope. Okay, so it's naturally give you that by extension line bundle. And part 3 of the theorem. So if I fix L and I vary my lambda, so I get a coproduct. The coproduct is from dp L of lambda to dp of L lambda 1, twisted tensor using theta of dp L of lambda 2. And so this coproduct has to do with the inverse of stable envelope. Okay. All right, so this theorem is not surprising. And so as a consequence, So under the formulation, so I look at these coherent shifts on my Hilbert scheme. So there's a monoidal structure. I can trace it by this theta. So this guy is a monoidal category by the lemma, because this theta is a bi-extension line bundle. And in this category, I got this bialgebra object. So I have my coha, and so I have those modules dp's. So this is a bialgebra object in it. Okay, and so now, so the definition or proposal is, so I define the category of lines to be the derived category of modules over this big algebra, big bialgebra. This guy, modules. Let me quickly give you an example to show you this is something concrete, then I can move to the von Grassmannian part. Okay. So, so the gadget appeared in the theorem looks very abstract. So actually, this can be very concrete. So for example, I take the quiver to be type A1. And this Hall algebra, by doubling it has to do with the Yangian of SO2. And so if I fix my co-weight to be the first fundamental co-weight, omega 1 check. And in this case, so the dp of L omega 1 check. So this, by definition, is the critical cohomology of the quiver variety, which is T star Grassmannian of V in L. And so this guy has a non-trivial function corresponding to the W. So this guy can be identified as, so I have the symmetric power L of C2. So this guy is a irreducible representation of SO2. And so this Yangi map to SO2 by evaluation map. If I do the evaluation pullback, so that's the representation as the Yangi. So this is by myself and Paul and Justin. And also in the work of Varnulo-Vassero, you can identify this critical cohomology with that representation of Yangi. So as Yangi module. The what? Yeah, so I should say the double of this. So I'm just, so the, right, so now you can see the algebra structure in my theorem. So that has to do with, so you have sim L1 and C2, and you times sim L2 and C2. So it goes to sim L of C2, so that's this map. And so now you can play around if you fix the L equal to 1, and if you fix omega 1. So if you fix lambda 1, lambda 2 to be omega 1, so lambda 1 plus lambda 2 will be twice of omega 1 check. And if you write down what is this co-product, this stable envelope from 1 to omega 1 check, to dp of 1 omega 1 check times dp of 1 omega 1 check. So as representation of Yang, so this guy is C2 times C2. And so this is the stable enveloping inverse. So that's the half of the R matrix for Yang inverse, so 2. So this is nothing but half of the R matrix of Yang inverse, so 2. Okay, right, so everything is concrete. So now the last 15 minutes, so I'll have to quickly move down to part 3. So the relations with Afan-Grassmannian. Okay, so the relative thing here is, so this global version of Afan-Grassmannian, so the Bellingson-Drinfeld version of Grassmannian. Right, so just a quick reminder. So the global Afan-Grassmannian has a base, so you can take to be any power of the curve. So maybe this is over a to the n. So if I have a bunch of points C, so the fiber here, the Grassmannian BD with fiber C, so that's the moduli of, so this is the moduli of pairs where you have a G-tosser together with a trivialization. Outside those points we are picking. Okay, so in particular it has a Bellingson-Drinfeld base. And oh my goodness. Okay, so right, so this Bellingson-Drinfeld Grassmannian over AN, so I can use my lambda to create some symmetric power. So this is over a lambda. So inside here, so there are Schubert varieties, this Grassmannian BD, fixed by this co-weight lambda. So this guy is by definition, so there's a global group scheme. You can think it is GO times T to the lambda, taking closure. Okay, so this is studied in Steven Drew's paper for the Afan-Schubert varieties. Okay, so so before I state my theorem, let me give you a general expectation. So the expectation is, so we have a proposal of the category of lines, which is the derived category of modules over this big thing, this dp. And so the expectation is, so there are some Wendel categories in. So there's a Wendel category in the subcategory, which is also triangulated category. And such that, so this Wendel category also has the H bar in it. If I take associated graded, so this should be equivalent to this dB of the BD Grassmannian R. So this is as triangulated categories. And so in this graded version of the Wendel category, so I can take the abelian heart. So this is equivalent to the perverse coherent shifts on the Afan-Grassmannian. So this is as abelian category. This is as derived category. So that's one of the conjecture or expectations. And second, so there are many choices of the Wendel category. So the one choice of the Wendel category has to do with the initial clusters. And if I switch the Wendel category to another Wendel category, so this should has to do with the mutations of the clusters in cluster algebra. Okay, so that's a general expectation for for the comparison with the Grassmannian. And so this part is also called the window shift. And so for the things we can prove, so let me give you a concrete statement. And so it turns out it's easier to fix on the orbit closure. So I'm gonna focus on the orbit closure. So this Grassmannian lambda closure. And so in this case, we can assume for simplicity that G is type ADE and adjoint type. Okay, right. So as I emphasized before, the cohi, if I take a double, so I get the Yanking of G, which has a parameter H. If I take associated gradient of this guy, that's the same as the universal enveloping algebra of the current algebra, G of T. Okay, and on the parameter side, so this Yanking acting on a bunch of modules, which I call it a dp L lambda. So if I take associated gradient, so I have the action of the current algebra on GER of this dp thing. Okay, so the theorem B is right. So there exists a unique isomorphisms of right. So that's a global statement. So I want functions on the base A lambda, and I also want the action of this current algebra GT. So there exists isomorphisms of this thing times the GT module, where I'm taking associated gradient of the dp with L lambda in it. So this is isomorphic to the global section of this Affan-Schubert variety parameterized by lambda, and I have this line bundle OL. So I have O1, that's a determinant line bundle, and I twist it by L times. So that's a global section of OL. So it turns out those two are isomorphic as a GT module, and globally they are over the same base, A lambda. Okay, such that, so it's compatible with the algebra structure on both sides. If I take the sum upon sum over L. So it means the following. Okay. So let me explain this. Right, so it means, so if I look at the Schubert variety, so Grassmannian with fixed co-weight, so this has a homogeneous coordinate ring, so that's the approach of this global section of GER lambda bar OL. If I take sum of L's. So the slogan is so that isomorphism. So this guy has a natural ring structure, and this isomorphism is compatible with the multiplication with a stable envelope on the dp side. Okay, so right. So the slogan is this dp h bar. If I sum over L, if I fix lambda, so this guy quantizes the homogeneous coordinate ring of the Afan-Schubert variety. Okay. All right. So that's a theorem we can show, and so maybe I mention some remarks. I'll be done. So the first remark is, so I'm not sure if you can fully appreciate the theorem. So this is a global statement. And so for the global statement, so there are geometries behind it. So the most important thing is for representation of those quantum groups, we always need an integral structure. So, so for example, my favorite method, equivalent localization, is forbidden here. So the equivalent localization is useless for the global statement. Right. Okay. So the second remark I wanted to mention is, so there's a Afan type of, so there's an Afan version of the Borel-Weil theorem. Means, so this is proved by Domansky, Fagan, and Finkelberg, DFF, and the twisted case by Zhou Hong and his collaborators. So the Afan version is if I take the global section of Grassmann of this orbit with section OL. So they can identify this with the concrete algebra of the current algebra. So this is isomorphic to the so-called global Dumazu module. Okay, so if you are interested in the algebra, so maybe you know what it is. The global Dumazu module, including the Kirillov-Reshetikhin modules. And in general, you can obtain by fusion product of the Kirillov-Reshetikhins. So the part, so the isomorphism here, so it's secretly three things. One is the GER of this dp ring. The other is global section of OL. And the third object is the global Dumazu module. Okay. Let's see. I have 2 minutes, so I can still give you one tiny example. Right. So if these two abstract, so we can look at the case when G is PGL2, and in that case, the Grassmann with the first fundamental co-weight omega-1 check. So this is nothing but P1. And so for the previous example, I said so this is dp with L omega-1 check H bar. So this is nothing but the symmetric power of L and C2. Right, so this as a vector space. So that's spanned by the homogeneous polynomials of two variables, L minus 1y, and so on. Okay, so if I take associated graded sum up of all L's of this span of this dp of L omega 1 check. So this is nothing, just the polynomial ring of two variables. So, so what the theorem is secretly saying, P1 equal to approach of CXY. Okay, but they are more structured than that. Okay, so I'll stop right here. Thank you for your attention.
Thank you very much for the talk. Is there any other questions for Professor Yang?
Yep.
There's a paper from about a year ago by Gayatto, Grigorev, and Lee, which
They talk about the coha and bimodule. I did read. Yeah.
and they sort of proposed that was a category of line operators. And I wonder if what you did is
So we did read that paper, and the only thing I can make sense from the paper is when G equal to C star, and when the N, the representation is C. And for that, I did have a mathematical way of understand what they're saying. And in general, I have to admit I don't understand what they're saying. And we did read the paper, and that's what we can come out.
kind of morally the same thing as what you're doing?
I wouldn't say the same thing, but are you laughing? Sorry, maybe we should talk in secret. I don't want to say,
Okay.
yeah. All right.
Any other question? All right, if not, let's thank the speaker again.
Thank you.
talk is turn numbers from algebraic geometry to differential equations. Okay, let's welcome.
谢谢First, I'd like to thank the organizers for the invitation. Today, I'm going to talk about the application of algebraic geometry in differential equations. In recent years, some birational invariants of algebraic geometry are generalized to differential equation. 10 numbers is one of the invariants. So first, I'd like to talk about the history of the application. I would like to start with Riemann's beautiful theory on the classification of algebraic curves. So in this paper, some important concepts in mathematics are introduced in this paper. For example, birational transformation, and the Riemann surface, and the genus of a complex algebraic curve. So in the classification theory, Riemann constructed the moduli space of curves of genus G. So he computed the dimension of the moduli space. So motivated by Riemann's study on algebraic curves, someone tried to study using a similar method to study differential equations. For example, Dabu studied this equation by using complex geometry. He said if you want to get some important information about the differential equation, this ODE, you have to study the complex solutions. You have to study the solution at infinity. So this means we have to study the differential equation on complex projective plane. The problem studied by Dabu is the algebraicity of the solutions. He proved that if in the solutions, if there are enough algebraic curves, then the general solution is algebraic. This means the general solution is a family of algebraic curves of genus G. So this is trying to using Riemann's method to study differential equations. The second great mathematician is Poincaré. Poincaré studied this equation by using complex geometry. He suggested to study ODE by using Riemann's theory on algebraic curves, essentially the moduli space of curves. He suggested to generalize some invariants of family of curves to ODEs. And the problem studied by Poincaré is the algebraicity. So when try to determine the algebraicity of the ODE by the invariants. So this is Poincaré's study. The next great mathematician is Painlevé. Painlevé studied this problem similar to Poincaré's, using Riemann's theory. Because in the 19th century, we only know one invariant of the family of curves. That is the genus, introduced by Riemann. So Painlevé tried to study the genus of a family of curves. He tried to prove that the genus is an invariant of differential equations. So the problem studied by Painlevé is if an ODE is algebraically integrable, this means the solution is a family of algebraic curves. Can we determine the genus G from the ODE? So try to find a formula from the ODE to compute the genus. Or try to, by using the invariance of the ODE to determine the genus in this paper. So Poincaré and Painlevé tried to prove that the genus is an invariant of ODE. The next one is Hilbert. Hilbert introduced the study of ODE by using the family of curves. So the number 16 problems is about the topology of algebraic curves and the surfaces. This is the first part. The second part is about the ODE. He tried to solve the problem on the limit cycle, the number of limit cycle the relative position. So this means the topology of the solution of the ODE. Why this one is due to algebraic geometry, this one is ODE. Why they Hilbert put these two problems together in the same problem? He explained maybe the two problems can be attacked by the same method. He explained the method, continuous variation of the coefficients. In our language, this is topology of families of algebraic curves. So topology of families of curves defined by ODE. Hilbert thinks these two problems, we can use the same method to attack it. So in algebraic geometry, we have some birational invariants. For example, for algebraic curves, the genus. For algebraic surfaces, the geometric genus, the plurigenus, PMS. We have also the Kodai dimension for surfaces. Kodai introduced this. The third one is the chain numbers for algebraic surface. We have 3 chain numbers. We have Luther's equality. So we have more invariants, topological invariants, Beatty numbers, Hodge numbers, Picard numbers, and something else. So for a family of algebraic curves, the birational model is a fibration from a surface to a curve. So we have the genus of a generic fiber. This is a smooth fiber. And we have we have geometric genus for a family of curves. We have Kodai dimension. We have chain numbers. So we try to generalize these invariants to ODE. So in 1960s, Riemann's moduli space are compactified by Deligne and Manfred. So we have a projective moduli space of curves. So this projective space provides us some method to define the invariance of the fibration. So from the moduli space, from the fibration, we have a classification map from the base to the moduli space. So Manfred called this map modular map. So this map provides us some birational invariance of the fibration. So this is called the modular invariance of the fibration from the moduli space. So for a family of algebraic curves, the birational model is a fibration on a surface. For the complex solution of an ODE, we call this the foliation on an algebraic surface. So on a surface, an ODE is defined by a rational one form, alpha. Here, this equation, the alpha is this. So for a family of algebraic curves defined by a rational function, so we can get a defining equation, ODE. The ODE, corresponding ODE is d phi equals 0. So this ODE is just this one. So this one is called algebraically integrable because the solutions, general solutions, is a family of algebraic curves. So Poincaré and Panevi tried to study the family of algebraic curves, try to generalize the invariance of this family or this algebraically ODE to general ODE. I will introduce the modular invariance from the moduli space. So for a birational transformation from S to S prime, a family of curves on S, you get a family of curves on S prime. An ODE on S, you get an ODE on S prime. Just consider the pullback. So birational invariance means the invariance is independent of the birational model. So modular invariance of a fibration means the invariance is independent of the base of the parameter. So the invariance is independent of the parameter. Because for an ODE, in the solution, you cannot see the parameter. So if the invariant can be generalized to ODE, it should be independent of the parameter T. So in order to define the M genus, the plural genus, and the codite dimension, we need to define the canonical divisor, a good canonical divisor of the fibration. We need a good minimum model of the fibration. So in general, we only study the relative canonical divisor for fibration. But this one is not good. If you use this one to define the genus, then it is not a birational genus, birational invariant. So what is the good canonical divisor? This is introduced by Serrano. The modification of this one. You minus some contribution of the multiple components of the fibers. So this one is good. So what is the minimum model for a fibration? Minimum model for a fibration means all singular fibers are normal-crossing divisors. And the fiber contains no redundant -1 curve. This means if you contract the -1 curve, you get still a normal-crossing fiber. So this one is redundant. You contract it, then you get a minimum one. So we have a minimum model. We have the good canonical divisor. Then we can define the geometric genus of the fibration, defined by this. And the M genus, the plural genus, by this. So we can define also the codite dimension of the fibration. Actually, the fibration, you can see the fibration, the codite dimension, the meaning. The codite dimension is determined by the genus of the fiber, generic fiber, and the isotriviality. So we have also numeric codite dimension. This is used. This depends on the codite heuristic decomposition. So if we have a low heuristic decomposition, then it's defined minus infinity. Then we can, the other cases defined by this. But for a fibration, the two codite dimensions are the same. So like here, for this equation, the solution is a family of lines. For this ODE, the solution is a family of transcendental curves. So we need to generalize the invariance here to here. So the first step is to define the canonical divisor of a fibration, of a foliation. For ODE, the solution, the complex solution, the set, is called the foliation. So we try to define the canonical divisor for a foliation. So if we, for a given rational one form alpha, we can define a divisor. The zero divisor means the one-dimensional zeros of the one form. And the polar divisor, then we can define the divisor of the rational one form. With this definition, we can define the canonical divisor of the differential equation, or the canonical divisor of the foliation. Ks minus the divisor of the rational one form. So the first result about the geometry of the foliation is due to Miałka. he proves that if Kf is not pseudo-effective, if and only if F is a family of rational curves, so this means the foliation is algebraically integrable. So the second step, this is the divisor of an ODE or divisor of a foliation. Then we need to define the minimum model of the foliation. So the first step is to define the singularities, the simple singularities. So in the fibration case, the simplest curve, simplest singularity is a normal crossing singularity. So what is the simplest singularity of a ODE? So we try to define it. For ODE, the singular point is the common zero of P and Q. So for a differential equation, we have, for a rational one form, we have this Jacobi matrix. So we have two eigenvalues of this matrix at P. The singular point is the simplest one, means P is a reduced singular point. This means the two eigenvalues is not both zero. So it's at least one is at least non-zero. The quotient is not a positive rational number. So this kind of definition is from ODE. And then we can define the eigenvalue of the singular point of the ODE, the ratio of this number. So by a sequence of Boolean ops, we can get from here, an ODE to here. Then we get a new ODE after a finite number of Boolean ops at the long-reduced singular points of F. Or of the singular point of the Pullback foliation are reduced. So this means we can get a reduced model of the foliation by a sequence of Boolean ops. Then we can define the minimum model. So we can use this model to define the Kodai dimension and the M genus. So in this definition, the two invariants are birational invariants. So this canonical divisor is good. Okay, then we can define the minimum one. The minimum one means the foliation is reduced foliation. The singular points are reduced singular point. There's low redundant -1 curve. If you contract a -1 curve, the new foliation is reduced, then this one is redundant. You contract all these kind of -1 curves, then you get a minimum one. So we can define so we can define the minimum model of a foliation. It's similar to the minimum model of a fibration. So this one is not, the minimum model is not unique in general. But for a family of, for a foliation of general type, the minimum model is unique. So let's see, what is the reduced singularity for a fibration? For a fibration, the normal crossing singularity defined by this. So the corresponding differential equation, like this. So we can compute the eigenvalues. The eigenvalue of this point is a negative rational number. So we call this kind of, for a foliation, if a singular point, the eigenvalue is a negative rational number, then we call this singular point algebraic singular point. So algebraic singular point. So for the definition of the invariance, we only need to consider the algebraic singular point because everything should be algebraic in algebraic geometry. Okay, Miyaoka studied the canonical divisor, the pseudo-effective, if and only if F is not a rational tensor. So if F is not a rational tensor, then rational curves, a family of rational curves, then we have Zariski decomposition of the canonical divisor. So use this decomposition, we can get some beautiful invariants. For example, you choose a minimal foliation, then define the codine dimension by this canonical divisor, the geometrical genus, the M genus, Zariski decomposition. The Zariski decomposition, the structure is very clear for a fibration, for foliation. So for a foliation, we can define similarly the numerical codine dimension. In the fibration case, we define this by using the Zariski decomposition. But in the foliation case, we can define it by same formula. So the structure of the negative part, N, is very clear. It is the connected component is a string of smooth rational curves. If you contract these curves, you get a singular point of a rational singular point of type A, N, Q. N and Q can be computed from the self-intersection numbers. So for foliation, here the decomposition is due to Cirello for fibration, Maquillan for foliation. So we have Zariski decomposition, and the structure of the connected component Ni is very clear. It's type Ni Qi singular string of rational curves. So if the foliation is minimal and it is algebraic, then it is just a normal crossing fibration. So we defined some modular invariants. They are birational invariants of a family of curves, and they are also generalized to ODEs. Next, we can focus on the 10 numbers of a family of curves. So for fibration, we have a classification map from the base to the modular space of curves. You consider the hypersurfaces in the modular space, kappa, delta, and lambda. Then you can define 3 10 numbers. They satisfy Lussell's equality. Essentially, we only needed to find the formula for 2 10 numbers. So the 10 numbers are modular invariants. This means it is independent of the parameter. So it is possible to generalize to ODEs. Modular means they satisfy base change property. If you consider this base change, then the 10 numbers are proportional to the older one. So this property means the base change property or the modular property. So for a genus 1 fibration, could I find the formulas to compute the 10 numbers? For example, the first 10 number is always 0. The second one is the degree of the GI function with respect to the parameter. And could I find a new formula to compute the 10 numbers, the second 10 numbers, by using the singular fibers? For example, here, new 2 means the number of singular fibers of type 2. The coefficient is the contribution of each singular fiber of type 2. So he get a formula by using the contribution of singular fibers. So for genus 2 fibration, Horikawa and Xiao obtained the computation formulas like this. First 10 number, second 10 number. shall define the singular index of a vibration. So it is some index. Shall, for general vibration, for any genus, shall obtain the slope inequality, the two term numbers, between the two term numbers. He defined the slope, lambda f, the slope of the vibration. So from this formula, we can say that the minimal slope of a vibration, vibration is 2. For genus 2 case, the maximum solution is 7 here. So for higher genus, so about 30 years ago, I get the formula for alien vibration, alien genus. So I introduced the 10 numbers of a singular fiber. This is the local contribution of the singular fiber to the global 10 numbers. Then we get the formula. The 10 numbers, here in the middle is the relative 10 numbers. This part is the contribution of singular fibers, the local 10 numbers. Then we get the formula. This is a generalization of Kodayar's formula. Okay, let's see the meaning of the 10 numbers. So the vibration is constant moduli. This means the smooth fibers are isomorphic to a fixed curve. So this can be characterized by the 10 numbers. So the Kodai dimension determined by the genus of the fiber and the 10 numbers of the vibration. So in this case, Kodai dimension is not a Liu invariant. So how to generalize the 10 numbers to ODEs? So this means we have to find the formula of the 10 numbers by using the data of the ODE. If you find this formula, then you can generalize the 10 numbers to ODEs. So the first step is to try to find a formula, a Liu formula to compute the 10 numbers. The Liu formula uses the data of the corresponding ODEs. So this is not difficult because we have a formula to compute the 10 numbers. So we have to use the minimal foliation, minimal model of the vibration or foliation. Use the Zariski decomposition. Then rewrite the formulas in terms of the decomposition and the contribution of the singular points. So I just say the connected component Ni of the negative part. The structure is very simple. It is a string of smooth rational curves. And the type Ni and the Qi are determined by the self-intersection numbers using this. Now we can write, we have to define some arithmetic functions because we need to consider the algebraic singular point. The eigenvalue is a negative rational number. So we have to define some, for this function beta lambda. Only a rational number has contributions to this one. For others, there's no contribution. And chi, this is a dedicated function of the real number. Then we can rewrite the formula of the 10 numbers. So for example, the first 10 numbers, the formula here is the canonical divisor. This can be generalized to foliation. The eigenvalue of the contribution of the eigenvalue, this works for foliation. So here, this is the contribution of the local contribution of the singular point of the negative part. So this formula is very simple. the self-indexation number of the canonical divisor plus this number, the contribution of the connected part of Ni. The second one is also, the formula is simple. The contribution of the singular point not on N, not on the negative part. But the point should be algebraic because otherwise beta is 0. So we only consider algebraic singular point, the contribution of this singular point. Then we have chi. Chi can be defined by some other formulas, but we use this one. This is simple. Okay. This is the definition for a foliation. Here is fibration. Here is foliation. The formula is the same. So the 10 numbers are generalized to ODEs. So there are some nice properties of the 10 numbers. For example, they are both positive, non-negative rational numbers. The first 10 number is equal to the volume of the foliation. They are non-negative rational numbers. For fibration, the two definitions are the same because we use the same formula. And if the genus is 0, the fibration, the genus is 0, we have low theoretical decomposition. So we need to use other formulas to compute the 10 numbers. Because we know the 10 numbers are all 0, so we don't need to find the new formulas. Then we can define the slope for foliation of general type. Because for this one, the first 10 number is positive, chi is positive, so we can define the slope. From Shell's slope inequality, the maximum slope is 12. The minimum one is 2. In the genus 2 case, the minimum one is 2. But for a foliation, non-algebraic foliation, transcendental foliation, the 10 number is also a non-general type, a general type case. The first 10 number is positive, chi is positive. And the slope, the maximum slope is 12. This is from Noether's equality. We don't know the minimum one. So this means we have to find the slope inequality for ODEs, transcendental ODEs. So we conjecture this minimum one is 1. In the algebraic case, the minimum one is 2. But in the transcendental case, we conjecture the minimum one is 1. We have an example, the slope is less than 2. So less than this minimum slope. But we don't know the minimum one. So let's say how many invariants are generalized to foliations, to ODEs. Could I dimension M genus and the 10 numbers and the volume, Shell's slope, and the genus. The genus, Poincaré and Panay try to prove this one can be generalized to ODE, but unfortunately this one cannot be generalized. There's no genus for a foliation for a ODE. So because our invariants, the 10 numbers are, for general type foliation, the 10 numbers are positive rational number. So we have problem, the minimalities about the slope of the 10 numbers. So for the slope, for algebraic case, the minimum one is 2. But for the transcendental case, we don't know the minimum one. So we need to find the slope inequality. For 10 numbers, we don't know the minimal volume. The algebraic case, non-algebraic case, maybe this one is less than this minimum one. Also for trend numbers, we don't know the minimal trend numbers for general type fibration or general type foliation. So finally, I would like to talk about the application of trend numbers in the Poincare problem and the Panevi problems. Poincare problem is try to use the invariance of an ODE to determine the algebraicity. Panevi's problem is try to use the invariance of the ODE to, if the ODE is algebraically integrable, the solution is a family of curves of genus G. Panevi try to determine the genus by using the invariance of the ODE. Unfortunately, there are counterexamples to the two problems. This later constructed the counterexamples. They constructed some ODEs on the plane, and they have the same degree, the same type of topological type. But on the other hand, by using the trend numbers, we can get some positive solutions to the problems. So we need to compute the trend numbers of some foliations. For the non-general type case, the Kodai dimension is less than 2. This is equivalent to the variation of the first 10 numbers. So the first 10 numbers are all 0 below. But how about the second 10 numbers? So in the transcendental case, the second 10 number, we computed this. The second 10 number are always 0. For the algebraic case, only one case, the second 10 number is non-zero, is positive. This is a family of elliptic curves, non-constant elliptic curves, non-constant moduli. For the general type case, so the important invariance is the slope of the foliation, the ODE. So the important invariant is the slope. The second is if the foliation is a fibration, so we have the genus. So the slope can be generalized to foliations. The genus, we cannot generalize this. So this is a invariant of the ODE. So from this table, we can say that if the slope is less than this number, the genus must be 2. So this means the genus is determined by the invariant of the ODE. So if the slope is less than 3, the genus is also determined. If the genus is less than 4, this shows slope inequality. This means the genus is bounded. If the slope is at least 4, the genus is unbounded. So this is a solution to Panevi's problem. Try to determine the genus by using the invariant of the ODE. How about the trend numbers? The trend numbers, only in genus 2 case, we have the optimal minimum model. For other cases, we don't know the minimal one. For the transcendental case, so we conjecture the minimal slope is 1. We have examples, the slope is less than 2. So we don't know the other lower bounds. Let's go back to the problems, Poincare's problems. So in some cases, we know Poincare's problem has counterexamples, but in some cases, the solution is positive. For example, in the first case, both 10 numbers are 0. From this latest counterexample, we know that in this case, we cannot determine the algebraicity by using the birational invariance. But in the second case, first 10 number is 0, second 10 number is positive. Then this is algebraic. The foliation is algebraic. This is a family of elliptic curves, non-constant moduli. So this means in this case, the solution is positive. But if the trend number is positive, first trend number is positive, this means it is a foliation of general type. The slope is less than 2. By using Shell's inequality, we know this, in this case, it is not algebraic. So we know the algebraicity. Only in this case, we don't know. The slope is between 2 and 6. If the slope is bigger than 6, at least 6, by Linslater's counterexample, we know in this case, we cannot determine the algebraicity. So in some cases, we cannot determine. But in the other cases, we can determine the algebraicity. We say the Pannevis problem. If the foliation is algebraic, if the ODE is algebraically integrable, we try to determine the genus by the birational invariance of the ODE. So in the first case, if it is algebraic, the genus must be 0. So it's determined. The second case is determined. In this case, it's determined. If the slope is less than 4, we can determine the genus in some sense. This is Shell's slope inequality. But if the slope is at least 4, maybe well, we cannot determine the genus because it is unbounded. How about the slope minimal trend numbers, minimal volume, minimal trend numbers? So if we prove that if the geometric genus is at least 2, the minimum one is 1/2. In the algebraic case, we get some lower bounds of the trend numbers. But only in the genus 2 case, the bounds are short. But the others, we don't know. So finally, so in the morning, in this morning, Chen Meng talked about the lossless inequality between the geometric genus and the trend numbers. For foliation, we have similar inequality. So for foliation of general type, this is our lossless equality. This is optimal. If this equality, if C1 squared is not equal to the minimal, the lower bound, we have a better one. For a fibration, the algebraic case, the lossless equality is better than this one, the general case. Both are short. So next problem is to try to generalize Shell's theory on genus 2 fibrations to ODEs. This means we need to classify ODE of general type with a small slope. The time is up. I stop here. Thank you.
Thank you very much for this nice talk. Are there any questions or comments? I have a question about the minimal volume or slope. Is it must be positive? You proved, or?
No, I don't know.
But you guess this should be 1.
Yeah.
But you don't know if.
Maybe it tends to 0. I don't know.
Okay. Any questions or comments? If no, let's thank speaker again.
谢谢。
Nanjing University. The title of his talk is on the growth of endomorphisms in algebraic dynamics. Let's welcome.
Thank you very much for the invitation. So it's my great honor to be here for sure. I like to speak in Chinese. The reason is that because during the COVID, I'm kind of isolated and there's no chance to speak Chinese. So after some years, I think my Chinese becomes poor and poor. Considering my English is not good either, so I have to choose one. So if you don't understand Chinese, I apologize for that. So 我今天就是讲这个所谓这个代数动力系统这个里面的这个自态射的这个增转力的问题。其中第二部分是和复旦大学这个江晨老师的一个合作。当然他明天也会讲一下他自己的近些年在这个follow threefold 上面一些工作。他在明天下午会讲。那么我报告主要是讲一下我在这个方面的两个工作，就是一个就是这个所谓的这个正商的这个自态射，还有一个就是零商的，就是我们会在这个代数动力系统里面考虑这样把它们分成这样两类的一个问题。在讲这两个具体的工作之前，就是给大家简单介绍一下这个背景啊，就是这个什么叫做代数动力系统。就是这个地方是主要背景是从这个高维的这个辅动力系统来的。所谓一个代数动力系统，我们指的就是这样一个对，就是你有一个代数簇 x 和它上面的一个满的一个自态射 f。当然有的时候呢，如果可以更进一步的考虑这样一个只是一个游离的一个自营射，但是这个会更困难一点。通常目前我主要考虑的还是这个morphism。然后对于这样一个 pair 的话，我们一般会考虑它的一些所谓的这个动力学上面的一些behavior。那么具体来说，我们可以考虑下面这样一些变量，就是赋予这个系统啊，就是最重要的一个变量，基本上就是这个所谓这个拓扑商。这是刻画这个系统的一个复杂度的一个非常重要的一个变量。那么接下来除了它之外，我们还会关心它的一个所谓的这个迭代图像它的这个体积的增长率。这个和它这个商啊其实联系非常紧密。这个变量叫做这个我们把它叫做个 log f。这是由 Gromov 引入的。除此之外，还有一个非常重要的一个概念，就是这个所谓的动力次数。它刻画的是我们这里这个 f 它的这个次数增长率，它这个 f 它的这个次数的这个增长率。这叫做这个动力次数。除此之外，还有很多其他的变量。那比如说有些算术的，那在这个报告里面我就暂时不做过多的介绍了。我就简单画个这样一个图，给大家解释一下我们所谓这个代数动力系统，就是它大概在这个地图上就是这个位置。就是我们知道这个代数几何和数论的一个交叉，就是这个算术几何啊。然后在2000年开始的时候，这个由 Seelman 他的这个 score 引入的这个算术动力系统，基本上就是这个数论和动力系统的一个交叉。那我把这个所谓这个代数动力系统放在这样两个交叉里面，就是它就是一般来说就是这个在代数几何的这个代数簇上面做一些动力学的一个研究。好，那首先我们回顾一下这样一个在高维的辅动力系统里面一个非常重要的一个结果啊，它是由Gromov 在77年和 Umid 87年他们两个的一个结果的一个合并。他说的是下面这件事情：假如我们给了一个辅的这个光滑的一个摄影簇，假如维数是 d， 然后你有一个满的一个自营射，或者就是 holomorphic 的这样一个 map。我之前说的这个对于这样一个动力系统，它的这个拓扑商是它一个非常重要的一个变量，这里叫做 h-top-f。然后 Gromov 证明了这个变量它是被它引入了这个所谓这个 log 迭代图像的体积增长率给控制住，它比较小。然后这个东西呢，它是一个代数的变量。然后从它的定义，天然的我们可以不难发现，它会比这个所谓的这个 h-ag 这里叫做代数商也来得小。 这个 HX 是这样定义的，就是我们考虑这个自态式 F 在它的这个上通道环上的这样一个拉回作用的这个谱半径，再取个对数，就把它定位成这个代数上。所以格罗莫夫证明这样一些不等式。然后优美定呢，在10年过后，它证明了另外一个不等式，就是这个代数商又比拓扑商来的小。那结合他们两个的工作合在一起，现在我们就知道，对于这样一个辅的系统啊，那么这些变量都是相等的了，就是拓扑商等于 log 等于 h 代数商 HX。好，这里我说的这个用这个 rule 表示它的这个谱半径。所以通过这个定理，我们现在可以知道，就是这个动力系统里面这个拓扑商，如果在我们这里这个设定下，它其实也可以把它看成是一个代数变量，代数不变量。所以我们可以用一些这个代数几何里面你的上通道理论去研究它。那么接下来就是在刚刚这个定理里面我说的这个右边那个谱半径那一块，它这个谱半径其实就把它抽象出来，就是给它一个定义，因为它非常重要，我们把它叫做这个开次的动力次数，记作这个 lambda kf。它可以有一些等价的定义，比如说这里你也可以用这个相交数来定义，就是考虑这样一种相交数，你取一个 ample 的一个除子，然后用这个 f 迭代的拉回它，去考虑它这个体积。它随着 n 增大的话，这个增长率就是这个动力次数。它用一些简单的线性代数的知识，它也等于这样一个线性变换的这个谱半径。就刚刚我们考虑的是你这个 f 在上通道上面的拉回作用，你也可以考虑它的这个代数 cycle 的这个空间。这个 n_k 指的是余位数为 k 的代数 cycle 抹掉这个数值等价关系，得到这样一个有限位的一个有限阿贝尔群，你在 tensor R 得到这样一个线性空间。所以这些变量都是一些都叫做这个 lambda k。特别的这个 lambda k， 你从这个定义里面就不需要，如果你不去看它的上通道的话，它也可以是在任何的特征下都可以定义的，在正特征的时候也可以定义，就不需要一定要在这个辅的。那么接下来就是有这样两个自然的问题，就是在刚刚的定理里面，因为格罗莫夫、优美定他们都是假设我这个代数粗是辅的。那如果把这个辅的换成正特征域，像我刚刚说的，你换成正特征域的话，它这个 lambda k 还是有定义的，就是比如说通过这个相交数来定义，对吧？然后我们会问刚刚这个定理是不是有一些类比？其次的话就是如果我这个商是零商的话会发生什么？就是那接下来我主要就是关注这样两类系统，一个是在这个正特征的这个代数动力系统，其次就是这个零商的这个代数动力系统。在这两个方面的话，有这样一些方向去考虑。第一个就是有这个Triennial，他在10几年的时候，也大概16年的时候，他提出了一个所谓的这个把这个唯一的黎曼猜想做了一个动力学的一个推广。等一下我会详细解释一下这个解释啊。然后其次的话，大概在2020年左右的时候，有这么几组这个数学家，他们就是考虑这个零商的动力系统，就是考虑了这个本来是迭代图像的这个增长率，但如果是零商的话，它只会有这个多项式的增长，所以它会考虑这个多项式的增长率，这样一个变量。然后在林学庸、Augusto 和张德奇他们的后续的工作中，他们发现这样一个动力学里面的这样一个体积增长率的这样一个变量，它和这个非交换代数里面的这个Galfand 的 Kirillov 维数这样一个所谓的 GK 维数是有紧密的联系，基本上就是它们俩是等价的。好，然后那么接下来先看一下这个在正特征的时候，如果你有一个正商的一个自态设，那么这个我刚刚说的这个所谓的这个Triennial它这个建议的这个所谓的这个唯一的黎曼假设的这个动力学的推广指的是什么？就是首先我们回顾一下，就是这个经典的这个问题，后来是等林证明的。他关心的就是如果你有一个定义在有限意义上的这个几何光滑的这个摄影簇啊，维数是 d， 然后考虑它这个 Frobenius 的这个 anomorphism， 那我们知道这个x 它的这个FQN 点的个数和这个 Frobenius zone 的这个 trace 是有关系的，就是用这个 trace formula。 你把这个点数，把这个点的个数拿出来，造成这样一个生成函数，然后再取一个这个取了这样一个指数函数过后，这个称为它这个 zeta 函数啊。这个 zeta 函数用这个格罗廷格和阿廷发展的这个平展上等量理论，现在我们知道，通过这个 trace formula 呢，它可以写成这样一个交错乘积。这里是通过这个 Frobenius 的拉回作用生成的，这样考虑它这个其实是个反的这个特征多样式，基本上是等价的，但它是这样一个交错乘积。所以它通过有了这个平展上等量理论过后，我们很容易就直接得出这个zeta 函数是个有利函数的。那这个是本来韦伊猜测的他说这个 zeta 函数是个有利函数。虽然 de Vaux 在没有这个平展上等量理论之前，他已经证明了。当然，利用这个平展上等量理论，很快就可以一下就可以得出来。那么接下来最关心的一步就是我们关心的是这个所谓的这个黎曼假设，韦伊的黎曼假设，它关心的就是这个 Frobenius 拉回作用它的特征值。这个是等林在74年证明的，就是说这个 Frobenius 拉回作用，这时候这个是真正的一个特征多样式了。这个特征多样式是整系数的，与 L 无关，系数与 L 无关，然后它的所有的特征值的这个当然是代数整数了，它的Archimedean 的这个绝对值，就是把它嵌入到 C 放到 C 里面看，它这个绝对值都相等的，就是等于这个 Q 的2/r1次方。Q 呢是我原来的这个最开始定义 x 的这个有限域的这个有限域 FQ， 所以这个是它这样一个这个定理，给大家回顾一下。那么接下来就是我们想把这个定理啊，就是有一个在动力学意义下的这个推广，就是如果把这个 F Frobenius endomorphism 换成其他的任意的一个姿态设，对吧？然后你也可以考虑这个姿态设它在这个上等量环上的这个拉回，不过这里我们当然也是取的这个平展上等量，然后你考虑它的这个谱半径。那这个就是跟我们刚刚说的 Gromov-Umedin 这个定理里面定义这个动力次数是一模一样的东西，就是有这样一个动力次数。那只不过这个时候呢，我们有两个动力次数，就是之前在特征0的时候，这两个动力次数定义是等价的，但是呢，在特征 P 的时候呢，我们发现就是这样两个定义你都可以定义，但是它们俩是不是等价的？却不是一件非常简单的事情，就是一个呢，你就是像之前一样，你拿用这个橡胶数来定义，你取一个安保除子，然后去用 Fn 的迭代去考虑这样一个橡胶数的一个增长率，它也等于我这个Fn 的拉回作用在这个代数 cycle 空间上的这个增长率，这是用这个代数的方法定义的，然后也就是说用cycle 或者橡胶理论定义的，把它叫做 lambda k。另外一方面，你可以我完全仿照这个 Gromov-Umedin， 就用这个上等料，只不过这个时候我们用平展上等料。你用这个平展上等料定义，考虑它在上面这个增长的这个范数增长的这个增长率，把它叫做 chi i。那他就问这两个定义是不是等价的？所以这就是他的这个问题，他猜测这样一个两个东西应该是等价的。这个最开始是他在16年他的这个preprint 是在16年，当时我在新加坡读博，他去那里做了个报告，他讲的是这样一个问题，但是呢，当时我完全没有任何的感觉，我也不知道这个东西就像正常听报告一样，就听了就完了。然后在后来我做博后，然后在做另外一个问题的时候，然后somehow就又回过来，就是发现哎这个问题好像跟我现在做的有点关系，然后我又回去考虑他这个问题，然后就是做了一个 case， 就是阿尔贝尔错的这个情形，那这就是接下来马上要讲的一个结果。所以他猜测这两个东西是等价的。然后这个在对于辅的情况下，这两个东西等价是比较显然的，就是用一些简单的比较经典的这个辅动力系统的一些知识就可以得到它是相等的。因为他自己本身初朗他自己也是辅动力系统出身的，所以他有这个辅动力系统的背景，他知道这个东西在什么时候它相等。然后除此之外，刚刚我们说的这个为什么它是这个韦伊的黎曼假设的一个推广？因为如果你把这个小 f 换成就是 Frobenius， 那这两个东西相等的，这两个东西相等指的就是 exactly 就是这个韦伊的黎曼假设。也就是说我刚刚说的这个初朗的这个猜想 DDC 猜想，就是动力次数比较猜想，它能推出这个韦伊的黎曼假设。 因为刚刚我们说这个唯的黎曼假设指的是我的 Frobenius 这个在平点程度上拉回作用的特征值是我们想要的这种 Q2的 Q 的 I 除以2次方这样一个东西。但如果你现在默认刚刚说的这个 Tron 那个猜想是对的，那么我现在就知道，我们想要去证明什么呢？就是证明它的所有的特征根啊都是只要你用这个捧将来对偶，我们只要证明它的这个所有的特征根它有个上界是小于等于 Q 的2分之 I 次方就行了。然后你再用个简单的这个这样一个所谓的这个用这个乘积促 x 乘上 x 这样一个技巧，就可以把这个问题再约化到只要证明偶数界的这个上统量，就是你只要可以考虑 hi2k， 就不是所有的 hi 了。那对于这样一个问题，把它约化到这个过后呢，这个就是基本上就是刚刚说的这个Tron那个猜想，因为它猜测这两个东西相等。如果你现在假设它相等了，然后右边这个 lambda k 这个变量对于 Frobenius f 的话，你去计算它是很容易算的，就是根据定义就直接出来，它就是这个 q 的 k 次方，所以这个是根据定义就直接有了。然后如果你默认这个东西是对的，那么你合起来就知道了 chi2kf 是等于 q 的 k 次方。然后但是呢，你现在要证的是 chi2kf 是小于等于 q 的 k 次方，所以你有这个它的猜想就能推出这个唯的这个黎曼假设。好，然后除了这个非常不平凡的这样一个证据，就是黎曼假设对的，那除此之外呢，还有一些conjectural 的猜测性的一个证据啊，就是 Tate 在63年的时候，他的一篇文章，就是他引入了他现在非常重要的这个 Tate 猜想的这篇文章里面，他还有另外一些猜想，其中有一个猜想就是他猜测这个用我们现在的语言就是这个 DDC 的猜想呢，是对于这个所谓的极化的这个自态射也是成立的。因为最开始这个极化自态射的概念是由这个塞尔在60年引入的，塞尔在59年给韦的一封信里面考虑了这个特征零版本的韦的猜想，然后引入了这个 polarized endomorphism， 他证明了对于特征零的 polarized endomorphism 这个韦的猜测这样一个类比是成立的。所以呢，然后泰特呢就进一步再猜测这个 polarized endomorphism 对于正特征也对，就是所以这个猜想是63年他猜测这个东西呢比韦的这个猜想还要更广。等零呢只是证明了一个特殊的这个 polarized 这个自态射，就是这个 Frobenius。泰特这个猜想是比较这个猜想呢是为什么他可以这样猜？因为如果你假定所有的这个标准猜想，然后你再用一下这个塞尔的这个论断，就可以也是可以原封不动的推出来这个黎曼假设对这个 polarized endomorphism 也是对的。那除此之外的话，还有就是在13年的时候，诺和施密马斯他们两个人这是首先证明了，如果是二维的时候，如果是 automorphism，那么我们刚刚说的这两个这个所谓的这个动力次数比较猜想 DDC 它是成立的。对于二维的话比较简单，就是你只用一个 case， 就是你要证明 λ1等于 chi2， 就是所以他们用这个曲面的分类理论是可以把它证明出来。然后最后就是提出这个猜想的这个 Tron 他自己证明了，如果你取最大值，所有的这个 chi2 你取最大值 ，λk 也取最大值，两边的这个最大值是相等的。好，那么然后我自己证明了这样一个对于阿贝尔簇这个情况，就是如果对于阿贝尔簇你有一个满的自态射，那么这个我们刚刚定义的这两个变量，一个是 λk， 一个是 chi2k， 这俩是相等的。换句话说就是这样两个变量是相等的，就是你考虑这个 f 的这个拉回作用在平展上统量上面 h2k， 或者是在它这个numerical 的这个algebraic cycle 上面，这两个这个空间上面的作用，它的谱半径是相等的。对于阿贝尔簇的话，左边这个变量是比较好算的，因为你只要知道了 h1 上的作用，你在 h2k 上的作用基本上可以完全把它 recover。对于阿贝尔簇比较难的是右边你这个 nk 这个空间是不是很好去理解的？就是除了 k 等于1，就是你如果是除子空间还好一点，但如果 k 大于等于2的时候，一般我们目前还是不是很清楚这个n2，比如说 对一个 Arbitrian Fourfold 你这个 NR 是一些具体信息，但是我这里就说有个粗糙的一个理解，就是它这个拉回作用的谱半径是可以跟上农药是相等的。然后就是这个问题，然后我做完了过后，我才意识到这个其实 Triennial 在他12年在这个M 就是 American Institute of Mathematics 这样一个 workshop 里面，他其实问了一个几乎一模一样的一个问题，然后我这里刚刚顺带就是回答了他的这个问题。然后在做这个问题的时候，其实这个问题它是从接下来这个结果得来的，就是我为了证明上面这个结果，顺带就是发现了另外一个事情，就是对于正特征的这个代入错，我们可以考虑它的这个一个 endomorphism 在它这个上等量上的拉回作用啊。如果你是考虑比如说是一个 odd degree 的 cohomology， 比如说 H1，那你本来你在 H1 这个 Betti number 是偶数次的。所以，比如说你在一个低维的阿贝尔图上，你的 H1 是2D 维的，那么它有2D 个根，然后呢，这2D 个根它有一些这种所谓的奇偶性的一个性质，就是我这里证明的，这2D 个根刚好会落进这个第一个对里面，就每个呢都是刚好是一个辅两个共轭的辅数。那特别的，如果你这个就是一个10的根啊，那么这个10根的重数是偶数重的，所以这个就是。跟这个特征零的时候是非常相似的。如果比如说你考虑一个辅的代入错，然后你考虑 F 在它的 H1 上的拉回作用，因为 H1 有这个好久分解，可以分解成 H01 和 H10，它们之间刚好是满足这个共轭的关系，所以你有这样一个第一个根的话，这第一个根完全会满足这样一个性质，就是它们会落在第一个 pair 里面，每个都是互为辅共轭的。这个证明其实不是很难，就是基本上就是用一下这个黎曼洛赫阿贝尔图上黎曼洛赫，然后再加上这个我们知道这个如果是阿贝尔图，它这个自同代数它是一个半单里，Q 代数的话它是个半单的一个 Q 代数，然后我就把几个这个相当于是把几个表示给合在一起，就是你有这个你给了一个 endomorphism， 你考虑 endomorphism 在它的上动量上的这个表示，以及它在这个algebraic cycle numerical group 上面的一个表示，再跟它在它自己生存的这个空间，就是这个半单里代数这个空间上的表示，把它们几个做一个 compare， 所以就是可以得到我们想要的结果。这个本质上就是用这样一个性质，就是这个半单里代数的表示。然后就是我刚刚说的，如果是在 C 上面这样一个所谓的这个奇偶性的这个现象是显然的，不光对 H1。对任意的这个奇数阶的这个奇数次的这个双同样，它都是对的，因为你对一个奇数阶的这个双同样，你有这个好久分解。但如果是一般的话，在正特征的时候，这个 parity 这样一个奇偶线，也是可以从这个所有的这个标准测象里面得来，就是利用这是等令的一个相当于它的一个 remark。最后我需要提一下，就是在去年的时候，前年就是谢君毅他完全把这个 DDC 给全部证明了，就是我们刚刚说的 DDC 猜想，就是一个 endomorphism 它的这个两种动力次数是相等的，他完全证明了。然后只要你如果假设了这个 DDC 对 Frobenius 成立，能推出 DDC 对任何的自态设成立。所以最后就是还有可以考虑的问题就是考虑这个 DDC 对于一个有理自行设。就是这个 case 它还是没有被解决。好，这个是我现在讲的第一部分，关于这个正上的这个自态设它这个所谓这个动力次数比较猜想这个工作。接下来我们回到第二部分，就是这个零商的，如果是零商的这样一个自态设，那首先如果是零商的话，它肯定是一个自同构，就不会是一个 degree 大于等于2这样一个自态设的，所以我们现在就考虑是一个零商的自同构。那我首先回顾一下，就是这个刚刚说的这个 Gromov 引入的这个迭代图的这个体积增长率这个变量，就是它怎么证明这个拓扑商会比这个代数商小？它相当于是在中间引入了一个 log 这样一个变量，就是这个 log 指的是，首先因为你想要考虑的是这样一个动力系统，所以一个自然的想法就是，这可能是研究动力系统里面人 比较经典的一个想法，就是你把所有的这个迭代全部拿在一起，考虑 f 平方一直到 f 的 n-1，然后呢，你考虑这样一个乘积的这样一个morphism， 它是把 x 打到 x 的 n-1次方这样一个大的乘积空间里面，那映射就是把一个点映到它所有的轨道，直到这个n-1，然后你看它的这个 graph， 所以看这样一个这个 morphism 它的 graph， 这个 graph 是在 x 乘上 x n-1这个更大的一个乘积空间里面的一个 b 的一个子集，所以你考虑这个子集的它这个 volume， 它这里的 volume 其实指的就是在代数集里面这个 degree， 所以把这个伽马 n 是刚刚说的这个映射的这个graph， 然后考虑这个 graph 的这个 volume， 这个 volume 其实指的就是一个 degree， 然后考虑这个 degree 的这个增长，那这里它是的这个指数增长，所以你取 log 然后除以 n 这个limit sup， 这个东西你定义成 log f， Gromov 证明这个 h top 会比这 log 小，然后 log 又比 h egg 小。那现在我们刚刚说，如果我现在考虑是零商的，零商我们刚刚说这3个变量全都是0啊，都是0的话，那外面2个暂时不用管，中间这个如果是0的话，指的是你这个伽马 n 的这个 volume 增长是比指数来的慢，它增长率是会比指数慢。但是呢，你还可以考虑比指数慢的增长率啊，所以它有这个 sub exponential growth， 或者说其他的一些 growth，但实际上这里它真正的增长率是一个多项式增长，所以呢就会有我们会考虑下面这个就是这个伽马 n 这个 volume 的它这个多项式增长率，所以就是把 Gromov 这个 log f 给它前面加个 p， 就是 plov， 所以 plov f 指的就是这个伽马 n 的这个这个体积的多项式增长率。然后这里这个 volume， 也可以简单的用一下这个相加理论，就可以它其实可以把它转化成计算下面这样一个除子的这个最高次自交数，就是本来这个 volume 是伽马 n 的 volume 是在里面，你用一次你把 考虑在这些迭代的下的这个拉回下面的项，然后再做一个求和，所以这个叫做这个德尔塔 n， 这个德尔塔 n 这个除子的这个最高次自交数，所以就变成了这里就是这个 volume 就是这个德尔塔 n 这个 x 上的这个 x 上这个 ample 除子它的最高次自交数的增长率。对于这个零商的这个自同构。这里有一些简单的事实，就是如果你是零商的，它等价于你的这个第一个动力次数 λ1啊是等于1。λ1，我们刚说 λ1其实是考虑 f 在 n1上，就是这个 Laurent-Serre group 空间上的这个拉回作用，也就是说它的这个，因为它都是这个本来就是一个所以它这个拉回作用它其实是定义在 z 上的，就是整系数的特征多项式是整系数的。所以它所有的特征根都是代数整数，然后又是首一的，所以它的如果你的这个λ1相当于是它这个 spare radians 啊，如果你的普半径是1的话，那所有它的根啊都只能是这个单位根，所以你 up to some iteration， 其实这个你可以就是这个拉回作用它其实是个这个所谓这个 quasi-idempotent 的，你 up to 你 some iteration 这个你可以假设这个拉回作用其实就是一个 idempotent 的这个作用。所以它这个表示这个矩阵其实就是一个 idempotent 的矩阵。那为什么这个 plov 这个变量，它我觉得它有意思的地方在于，它不仅仅只是作为一个代数动力学里面的一个刚刚说的这个迭代图的这个增长率啊，它竟然也和这个 Artin-Tait-Vanderbilt 在90年左右引入的这样一个所谓的这个你有一个这样一个系统。然后呢，你考虑它这个所谓的纽齐次坐标环，就是如果你有一个 automorphism f， 然后呢，你考虑这样一个这个代数，这个代数呢是这个 bn 的值，是从它的这个就是你拿一个tensor 拉回 L， 一直tensor到 Fn 减1，其实就是这个 homogeneous coordinate 齐次坐标环，所以它相当于是把这个齐次坐标环给它用这个 F 给 twist 了一下。这个乘法的定义就有个这样一个自然定义，我就不定义了，然后可以让它变成一个代数。那对于这样一个它是个非交换代数，那对于这样一个非交换代数的话，刚刚说阿汀泰德他们证明了在2维的时候，这个非交换代数它的这个有一个所谓的这个 Gavron 的 Kirov 维数 GK dimension， 这个维数呢是有限的，当节点呢这个 F 这个作用啊是零商的。当然他们是用他们的语言写的，就是用我们现在的今天的语言就说它是零商的。然后这个结果他们猜测在任意维也对，然后在2000年的时候被Kira 他证明了，他证明这个确实是对的。这个任意维的这个 x， 它这个纽齐次坐标环这个非交换代数，它的这个 GK 维数呢是有限的，当节点呢这个是零商的 ，F 是零商的。这个 GK 维数刻画的是这个代数的它这个代数的增长率。就我们知道，如果对一个群的话，在这个几何群论里面，你可以去研究这个群的增长率，对吧？然后这个代数的增长率，就是把这个群的增长率再做进一步的推广。特别的，如果你这个代数是个群代数，那这个代数的增长就是这个Gelfand 的 Kirov 维数，就是之前我们知道这个群的这个增长。其次，他还证明了这样一件事情，就是如果我这个 F 是零商的，然后呢，他给出了这个它其实就是本质上证明这样一件事情，就是这个 GK 维数减1等于我们刚刚定义的这个 Prov F 这个动力学意义下的这个变量。所以这两个变量其实相当于是本质上是等价的。所以这也是我觉得这个变量是值得去研究的一方面，因为一方面是从这个非交换代数里面来的，另外一方面是这个代数几何或者说这个动力系统里面来的。那么接下来就是Kiel 他不光证明了太阳相等，他给出了这个 GK 上界和下界，他证明给出了这个 Prov 的一个上界是1加。那这里第一呢是开 F 类区块的约端块的那个最大的个数，最大的大小。对，你把它这个做约端标准型里面取的这个最大的那个块的那个大小是叫做 k 加1。这个变量有意思的地方在于，它其实与我们之前说的这个 F 的这个次数增长率是有关的。就是如果考虑 Fn 的这个增长率，这个 degree 1，就是它表示的是你拿一个安泡初子出来，考虑这个安泡初子在 Fn 迭代拉回拉回下它的这个体积的增长率，它其实就是这个 n 的开次方。如果你的前面的 k 加1是它的一个约端块的大小。好，这个是它的下界，我就略过，上界是我们马上要讲的。这是一个 remark， 就是它的证明方法就是之前我们说了，这个 Prov F 啊，它可以把它写成这个初子德尔 n 的最高次自交数的这个增长率。然后德尔 n 呢，因为我现在的 F， 你可以假设 F 就是 unipotent 的，所以它可以写成一个这个 identity 这个 matrix 加上一个 nilpotent 这个 matrix 幂零的 matrix。所以你把这个 Fi 给展开，然后再用一些组合的恒等式，最后可以把它改写成这样一个初子的和。改写的好处是，因为前面我们考虑增长率的时候，这是个本质上它相当于是个无穷求和，因为你要让 n 趋向于无穷大，你考虑增长率。但是你通过这样一个改写过后，现在变成一个有限求和，因为 k 是固定的，所以就只不过它的无穷的地方出现在了你这个系数这里。然后对于这个就是林学庸、奥圭索、张德奇他们在21年的时候，他们观察到了刚刚说的这个 Prov F 和这个GK 维数之间的这样联系，然后他们算了这样一个例子，这个 case 啊，就是如果是一个复环面，他们能把这个 Prov 具体给算出来，就是利用你这个 F 在 H10的这个作用下的这个约段标准型，它刚好可以写成这样一个平方和。然后他们就猜测，基于他们的例子，他们猜测 Prov F 是会被这个维数的平方给一致控制。不 ，x of f 一定 发考虑的时候，我也没有太注意。然后直到2年过后，然后在做思考别的问题的时候，然后回头发现这个才意识到这确实还是挺有意思的，就是以前没有意识到这个 plov它的这个真正的含义啊。然后首先第一个就是利用我刚刚说的这个，我在这个正特征阿贝尔图上前面那个工作，我也可以把他们刚刚这3位这么3位他们证明的这个复怀面的结果推广到任意的阿贝尔图，就是在任意特征。其次的话就是我刚说的这个和复旦的江晨老师的合作，就是我们相当于是完全把刚刚他们说的这个问题给回答了。就是我们的方法是，就是我们可以证明在任意一个这个低维的代数凑，如果我的这个 f 是一个零上次腾构，换句话说就是这个 fn 的这个增长率啊，这个次数增长率是大概是这样一个 n 的 k 次方这样一个增长。然后因为这个 f 是个自腾构啊，这个 k 一定会是个偶数，这个是大家都知道的。那么我们首先第一个就是我们把我们给这个 k 的一个已知上界，就是 k 会一定小于等于2倍的 d 减1。这个结果其实本来在特征零的时候是再早前有一些人已经知道了，然后我们相当于是给它的一个任意特征的一个证明。所以这个是第一部分。最主要的部分是第二部分，就是第二部分我们证明了这个 plov f 是小于等于1/2k 加1乘上 d。然后我们证明了这个事情过后，把这俩合在一起，那我们就知道这个 plov f 就会小于等于 d 平方了。这个证明这个东西啊，就是 plov f 为什么会小于等于1/2k 加1乘以 d。这个是就是我其实刚开始的时候算了很多的例子，低维的例子就是 d 当等于 k 的话，就是因为 k 是小于等于个乘。至于这个那些语言，其实我 C 语言什么我都已经忘光了，但是我就是去现学，就是大概知道里面会用一些什么循环啊之类的，然后你就去 Google 一下，你想要什么东西，让它把那语句给你。但现在我发现这些都没有必要的，如果你用这个 ChatGPT， 它很容易一下就把你那个code 给你了。Anyway， 然后在我算的例子过后，比如说当你的 d 小于等于20位、30位，就我想要的那个这个猜测都是对的。所以后来我们就想去把这个东西给真的证一下。然后证明的时候，我们首先要用到一个东西，就是我们要用到一个所谓组合里面的这个所谓的这个限制分割数，就是为什么这里会有一个这2/1k 加1，这本质上是这个1/1k d 啊。这个1其实是因为你只要他们那里也会出现这个1，这个1其实不关键，本质上是这个1/1k乘以 d， 这个1/1k d 这个东西是因为从这个组合里面这个限制分割数它有一个所谓的单峰性，就是因为这个单峰性导致我们想要去解方程的时候，就是你的方程的个数是足够多的。但是如果你超过这1/1k d 这个界限的话，你的方程个数就变少，就是你的方程就变得是不可能是想要我们得到那个零解。这是第一部分。那其次的话，真正的我们得到了这样一系列的这个方程过后，然后我们想去解的话，一个一个求解也很麻烦。我们最开始的方法很笨，然后后来我们发现这个东西其实竟然和这个李代数啊 S2 这个李代数它的这个李代数的这个表示是有关系的。就是我们想要去解这个线性方程组，这个方程组的系数刚好和这个李代数的这里面这个 Lefschetz 算子的这个表示矩阵是完全吻合的。因为我们想要证明一些矩阵是满质的，然后我们知道你 S2 这个表示矩阵 ，S2 的这个表示里面它的这个 Lefschetz 算子的这个表示矩阵都是满质的，所以通过这个部分，我们就可以把这个想要证明这个满质的这个性质给证明出来。所以最终把这俩合在一起， 的话就是具体来说就是你考虑一个 G 的 I， 然后你考虑这个 F 在 HI 上那个拉回作用，它的特征根呢是不是满足刚刚我说的这个奇偶性？特别的就是如果你的实根是不是一定的是偶数重的？那如果是 for business 的话，从等令的这个 VR 里面，就是我们现在都这个是知道的。如果是 for business 的话，如果不是 for business 的话，去年我考虑了一个 polarized morphism 的一个情形。我考虑是，对我如果是 polarized morphism 的话，这个也是对的，对任意的 x。但是其他的 endomorphism 暂时还不知道。另外一个问题就是，我在做这个关于这个 polarized endomorphism 它这个奇偶性的问题的时候，我发现了有一个很有趣的意思，就是这个有个所谓的这个牛顿在浩劫上面的这样一个性质。这个刚开始是 Katz 的一个猜想，在70年代被Mazer 证明的，就是对于 Frobenius 成立的，就是如果是 Frobenius endomorphism， 考虑它这个 Frobenius endomorphism 在平转生的上拉回作用的这个特征多项式，它是个整系数多项式。对于这样的整系数多项式，可以考虑它的牛顿多边体牛顿 polygon。然后呢，对于这个代数错 x 本身，它还有一个所谓这个 Hodge polygon， 它是从这个 x 的这个 Hodge number 来的，所以它是个几何的。然后这个 Newton polygon 是跟这个 Frobenius 相关的。然后 Katz 猜测，这两个 polygon 是有这样一个关系，位置关系。Newton 呢一定是在 Hodge 的上面。然后我发现这个问题也应该有一个这个关于 polarized endomorphism 的这样一个类比。所以你也可以问这个 Newton above Hodge 是不是对 polarized endomorphism 也对？这个问题如果是 abelian variety 的话，我这个是也。我去年在做这个问题的时候，这话不是光还可以问哈前degree 1就是 Fn 考虑这个 Hx 这个安保除子在 Fn 的拉回作用下的一个增长率。那这个时候你可以考虑 degree I， 你考虑 Hx 的这个 ith 自交，然后这个 cycle 在 Fn 的拉回作用下的一个 volume 的增长率。然后我猜测它应该是长成这样的，是 Ri 乘上 d 减 i， 但是呢目前也是还没有特别好的方法去证明这个事情。那这个就是我所有讲的东西了，感谢大家。
谢谢胡飞老师精彩报告。大家有什么问题？
我问个问题啊，就是你刚才说了Newton above Hodge的猜想
啊。
其实就是说刚才在德令跟牛顿猜想之前，就像你刚才说的塞尔写的他的一篇文章，提出来这个 polarized endomorphism。塞尔的 argument 实际上后来被格罗桑就引用，就基本上就是他们说，如果你假设一个 standard conjecture， 那么这个会猜想。
对。
那现在在你这个猜想里面，就是说，如果这假设 standard conjecture 成立，那是不是对 polarized endomorphism 有这个？
这是很好问题啊，这个我目前也不知道，但是确实是可以去考虑的。就像我之前说的，前面那个 parity 就是 parity 这个问题，等令就是它证明了，如果你假定所有的 standard 猜想，那这个 parity 是这个是成立的。这个是之前有一次开会我碰到 Eno， 我问他，然后他把我的问题就是问了等令，然后他写的这个letter 里面说的，如果是这个这一块的话，这块因为其实这个问题我也是最近刚开始想的，就是我还没有很好的这个理解。如果是假定标准猜想这个东西是不是对的？
这个也有点难说，因为比方说像
这些 F crystal 的一些 category， 但是 如果你把 f 换成 polarized，就感觉，不知道是不是，如果你只是 follow 它的话，你要引入一些类似的这种 category 啊什么的，感觉好像不是，我不知道是不是自然的。
您问好了吗？啊，谢谢。还有什么问题吗？大家？如果没有的话，那我们再次感谢 of this talk is crossing map, word crossing, and some application. Let's welcome.
Thanks so much for the invitation, and thanks so much for the introduction. It's my great pleasure to speak here. Today I'm going to talk about quasi-map word crossing and some recent applications. So before introducing the concept of quasi-maps, let's look at the very classical motivating example. So let X be a generic quintic hypersurface in P4. So we consider this one because it's a Calabi-Yau threefold. And the goal is to count curves in X. And why this makes sense is that if we fix, to get a finite number, if we first fix some topological data, for example, the degree and the genus, we fix those two numbers, then by some naive dimensional counting, we expect that there are only finitely many curves of this degree and in this genus. However, this is rarely true, even for generic X, because in algebraic geometry, we don't have too much enough freedom of deforming X. Related conjecture is Clement's conjecture, which basically said that you do get the expected result in gen 0, but it's expected to be not true. Well, the strongest version is not true, at least. In high genus, it's rarely true. So a better idea is to count maps. So let this mg be the moduli of stable maps. So this will be parametrizing maps from C is a nodal curve of genus G, and the curve class paired with the hyperplane class is a degree D, and plus some stability condition. So this stability condition will be the key to the talk today, but I'm going to talk about this later. And it is a proper, if you choose a stability condition suitably, it will be a proper Deligne-Manifold stack. It's not very far from being a space, but the problem is that it's highly singular in general. There are lots of obstructions. So by the work of Li Tian and Baron Fantacchi, so this space carries a canonical virtual fundamental class inside the child group of expected dimension. So the construction is of this class is kind of technical, but it is the intersection theoretic correct object to consider. It's kind of standard nowadays. I'm not going to explain the construction of this virtual cycle, but just to, if you never seen this before, to give you some idea what this should be, let's look at the genus 0 case. In the genus 0 case, if you consider the embedding X inside P4, we can compose a map into X with the embedding. Then we get an inclusion morphism from the mapping space to X to the mapping space to P4. So in this case, the right-hand side is very nice. It's actually a smooth and of expected dimension. So in this case, the virtual fundamental class is just the Euro fundamental class. And so inside this smooth thing, this possibly singular thing is cut out by a section of a vector bundle over this nice space. So if you think of this bundle, the fiber of this bundle over a point in this space is just the space of sections of O5 restricted to this curve C. And the defining equation for X, you put it back to the curve, it's an element in this vector space. So globally, it gives a section of this vector bundle, and the zero locus is precisely where the map to P4 factors through X, right? So although the section might be not transversal to the zero section, But if you do this correctly in the sense of intersection theory, the virtual fundamental class of this moduli of map to X is just equal to the top chain class of the vector bundle kept with the usual fundamental class of the right-hand side of the nice moduli space. Okay, that's a GS0 case. But in high GS, the right-hand side is also singular, and this is no longer true. Okay. So in order to calculate GN0 invariance, let's look at one example. The easiest example is when it's counting lines, this meaning that d equals 1. So in this case, the right-hand side is just the Grassmannian G25, and E is just the fifth symmetric power of the tautological subbundle dual of that. And it's a like classical exercise when you study intersection theories. By Schubert calculus, you can get the number, the correct answer to 2,875. Okay, that's how many lines we have on a general quintic. But for greater D, it's much more complicated. One way of the standard way of counting curves is to consider the torus action on P4. And so this induces a action of this torus on the moduli of maps to P4. And the vector bundle E we talked about before is equivariant. So we can use one can use a localization formula to explicitly give an explicit algorithm to compute any like the degree of this virtual fundamental class. The degree of the fundamental class is a virtual counting number. We can use that to compute. But as you can imagine, although there are only 5 fixed points on this P4, but once you take the mapping space, the fixed loci will be very complicated, parameterized by very complicated graphs. You can have one component of the curve mapping into one fixed locus in P4, and the other component mapping into the other fixed component connected by a P1 mapping to a one-dimensional orbit. So it's very complicated. And so it's very difficult to actually get any closed formula. But Giventhal and Lian they package those into closed formulas and verifying the prediction from mirror symmetry. So physicists have predicted the formula, but for mathematics, it's very, very hard to obtain that. Okay. So in order to explain, further explain the result, we need to set up some notation. So let me talk about Gromov-Schmidt invariance in general. So we first introduce some additional data to this modular space. So this is a variant of the moduli introduced before. So the difference is that we also consider markings. There are n mark points in the smooth locus of C, and they are assumed to be distinct. The rest is the same. And there are evaluation maps from the moduli to the X. X is referred to as a target space. So it's defined by evaluating the map at the ith mark point. And in general, if we are given like cohomology classes on X, and we are given like natural numbers, then the Gromov-Schmidt invariance written in this form is defined to be you first pull back the cohomology classes on X along this evaluation maps, then you cap with some powers of the psi class. Then you integrate against the virtual fundamental class. So here the psi i's are some tautological classes on the modular space. So the geometric meaning that there are virtual countings of curves with the incidence conditions and the tangent conditions. For example, if gamma I is punctually dual to some cycle, then basically you're counting curves mapping the ith Mach point into that cycle. But it's a virtual counting. Okay. And of course, this story works for any smooth projective X and also allowing orbifolds. So the G0 result can be stated as follows. So first, one has to define a very complicated formula. It's just a generating series of some Goromorphic invariants. So the exact form of this formula is not quite important for the purpose of this talk, but just to be explicit, I wrote it down here. So T is just some general element in the cohomology class, and the Q is some Novikov variable keeping track of the degree. And this is all about GN0 invariance. And then, of course, you can, for Calabi-Yau threefolds, if you can compute this J, actually, J at T equals 0, you know all these numbers, the degree 1, degree 2, degree 3, like rational curves. You know all these numbers. So the goal is to compute this function. But to compute this function, the answer is in terms of another function. The formula also looks complicated, some hypergeometric-like series, but valued in the cohomology of X. So H is the hyperplane class. Z is some formal variable, which will have a geometric meaning soon. And the mirror's theorem of given Triennial said that the J function is equal to the I function, but under the mirror map. The mirror map is some, in terms of this I function, can be computed explicitly, and is some invertible change of coordinates. Okay, it might look very complicated if you're not working in this area, but actually the story I want to tell is that we can like reinterpret this in another way using quasi-maps. Okay. So the first step is to see the I function, the complicated I function from quasi-maps. So let's forget about all those stable maps and et cetera, virtual cycles, et cetera. Let's forget about those. Let's just consider the very, very naive curve counting. So if you are like, if you're like a first-year student learning algebraic geometry, maybe the way you count curves is that you write down a map from P1 to P4 in terms of this 5 polynomials. They're homogeneous of the same degree D. And in order to define a map, we require that they have no like common zeros. The 5 polynomials have no common zeros at all. That way they define actually a map from this P1 to P4. Okay. And this is not proper, of course, because, well, we take limit that they can have common zeros. But let's just allow common zeros. Let's take the naive computation, which is that just the space of all f above, but instead of requiring they have no common zeros, require that they are not simultaneously zero polynomials. This is a much weaker condition. Right? And it's equivalent to saying that their common zeros are finite. Right? And of course, modulo the common scaling action by C star. So it's nothing but just a big project space, P to the 5D plus 4. Okay, because they have, for each polynomial has D plus 1 dimensional choices. Okay. It's very simple, but let's make it even simpler. So the objects parameterized by this one is a parameterized domain version of quasi-maps. They are not maps because when they have common zeros, it doesn't define a map, so they're called quasi-maps. Okay, it's that simple. And there's a C-star action on this moduli space. This time we still consider C-star action, but we consider C-star action on the domain P1 instead of the target space. It's action on the domain P1 by just mapping UV to TUV. Okay. It scales all the polynomials. And there are many fixed components, but much fewer. But we only consider the distinguished fixed locus, the most non-interesting one. So in this, a parametrize is just constant quasi-maps. So all the polynomials are monomials u to the d, constant multiples of monomials u to the d. They're proportional to each other. Okay. So this space is just isomorphic to P4. Right. It's very simple. And as before, the condition of we talk about P4, right? But we want the hypersurface. The condition of lying inside X is given by some vector bundle E, which is also easy to write down, but I'm not going to do that. Anyway, so in the spirit of Artier-Bolte localization, we only consider that component, but C-star equivalently. The contribution of that component should be, first we have the fundamental class of the component, then we have the equivalent Euler class of the bundle, but weighted by the equivalent Euler class of the normal bundle. Okay. If you compute that, it depends on D. It's a cohomology class on P4, and it has involves some equivalent parameter. So if you compute that, you can easily get this term. It's exactly just the I function term. Okay. Where Z is the so-called equivalent parameter. It's a generator of the equivalent cohomology of a point. Okay. I think this spaces and this localization has been considered way before quasi-maps, for example, by Giventhal and Liao. But today, what I want to explain that in the context of quasi-maps, we think of those special quasi-maps, the constant quasi-maps, u to the d, multiples of u to the d. Maybe let me write that down. So we have a P1 here. So we have so this is 0 and infinity. We have a constant quasi-map. It's given by a u to the d and a for u to the d. Okay, so this is to P4 or x inside P4. Okay. So we think of those. So it's not defined. For example, this is a point u equals 0. Maybe this is infinity and 0. So in the context of quasi-maps, we think of those special like quasi-maps as some rational tails. A rational tail is just a P1 like this. It's a Riemann sphere bubbling like this, detached from the main component of the domain curve. We think of that way. Okay. And I'll make this precise in a minute. But the slogan is that the automorphisms of these tails, you see that, so there's a special point where you have a common 0. We have another special point, which is a node connecting to the other components. The remaining part, well, fixing those 2 points, there's still a C-star worth of automorphisms. And that automorphisms of this rational tail via quasi-map walk crossing gives the contribution of this kind of rational tails to the Gromov-Fitting invariance. And if the whole thing is Gen0, you can like pick out the spheres one by one, then you get everything in terms of that formula. That's why this function gives the answer of counting Gen0 curves. Okay. So somehow you start with something, a domain curve like this. You have like a bona fide map onto this P4. Well, on this P1 is given by some F1, generic F1 to F4. But you scale that F1 to F4 by this C star action, by this C star action. And the limit will be the special constant quasi-map like this. And that contribution will give you the contribution of this thing to the Gormley invariance. Okay, that's a slogan today. Okay. Well, it doesn't make sense immediately because you don't have this C-star action, right? You don't have a special point here. You don't have a C-star action globally. And this bubbling can disappear if you deform this object. So it doesn't make sense immediately, but it makes sense in the context of quasi-maps. Okay, where am I? Okay, let's talk about quasi-maps. What are they? So let's consider a special case. Quasi-maps can be defined by for a much broader class of target spaces. But for simplicity, let's think of a hypersurface defined by equation f equals 0. Then, motivated by the naive counting before, a quasi-map to X is just a triple, where this Cx is a pointed nodal curve, and L is a line bundle on C. So in the previous example, it's just O of D on P1. And the phi I are sections of these line bundles, subject to the condition that, well, first, they are containing X in the sense that if you plug in these sections into the defining equation of F, it spits out 0. And it doesn't have to be a map, but it's almost a map in the sense that the locus where the sections all vanish is finite and away from the singularity and the markings. Okay, so generically, it's a map. So the points in the common vanishing of these sections are very important. They are called base points. And to define the stability, well, stable maps are special kind of quasi-maps. But we want different stability to get different, like, modular spaces. So to define the stability, the two key notions are the length of base points. In this case, they are just the common vanishing order of all these sections. So in particular, it's not a base point if and only if the sections do not vanish simultaneously, meaning that the length is 0. And we need a notion of degree. So for a subcurve, meaning that irreducible component, we say that the degree of this subcurve is just the degree of the line bundle restricted to the subcurve. And so now the key, the epsilon stability introduced by Kyokan-Fontaine, Kieman, Molik. So given a rational parameter epsilon, a quasi-map is epsilon stable if first it has satisfied the base point condition that the base point cannot be like, there could be too much accumulation of base points. There can be many, but they cannot accumulate too much. Okay. The second one is positivity. So the L to the epsilon tensor power, tensor this omega log, the log dualizing sheaf, is ample. So on the curve, just the rational line bundle being ample just means it has positive degree on each component. Okay. So let's analyze the second condition further. So we analyze the degree of this line bundle. So first, the L part is always non-negative. Otherwise, all the sections will be 0. The base points will be not finite. Right? And then the second part starts from -2 and 1 and 0. Okay. So the case -2 is too special. This means that the curve is just irreducible P1. So let's put that aside for a moment. So the most interesting case is the degree is equal to 1. For example, on this curve, it's a P1, but there's a node, so the dualizing sheaf has degree -1 here. So for such a case, it's called a rational tail. So it's just a P1 with one smooth P1 with one node or marking and nothing else. So in this case, the right-hand side has degree -1. So the whole thing, the condition that this is being positive just means that degree of this component is at least 1 over epsilon. You can compare this with the base point condition that it's also controlled by 1 over epsilon. So it's a trade-off. You can either have this kind of bubbling rational tail with some degree, certain degree, or you can contract it. You get some, and the degree becomes a base point, a common vanishing here. So it's a trade-off. At each point, you make a choice. You either allow a more rational tail or you allow more base points. The epsilon tells you which choice to make. Okay. Once you have, every time you take a limit, you have unique choice, you get a proper modular space. So there's a wall and a chamber structure and wall crossing phenomena. So for example, the wall at epsilon equals 1, well, to the right-hand side of that, so because this 1 over epsilon is smaller than 1, so this means that the length has to be 0, so no base points at all. And the degree is just positive is enough. So in this chamber, it's equivalent to the stable maps. And if you cross the wall, then you disallow, cross the wall at epsilon equals 1, you disallow degree 1 tails. You contract that to a length 1 base points. Because the total degree has to be remain the same, so you get a length 1 base point. If you cross the wall at 1/2, you contract further the degree 2 tails to length 2 base points. Okay. So, and etc. And if you fix the total degree, then obviously there are only finitely many walls at 1 over integers. So Kilcan-Fontaine, Kamen, and Molik, they show that the moduli of such objects are also proper Deligne-Montfort stacks with virtual cycles. So similar to Gourmand-Fine invariance, quasi-map invariance can be defined. Okay, and in GS0, if the whole curve has arithmetic GS0, then the whole curve is basically a tree of P1s. Then after this wall crossing to epsilon towards 0, to the left-hand side, you get an empty modular space, and all the contribution coming from the wall crossing contribution. Okay. So I obtained a geometric proof of wall crossing formula saying that the invariance in 2 adjacent chambers are equivalent up to explicit like change of variable, or there's explicit induction formula relating the invariance in adjacent chambers, and hence all the chambers give you equivalent invariance. And I'm not going to write down the formula, it's kind of complicated, but let me explain the geometry. So the proof is via the construction of some master space. So master space is a larger modular space containing both moduli. Suppose we are crossing the wall. The wall is here, so we have 2 stability conditions on 2 sides of the wall. We have 2 modular spaces. So I constructed a larger modular space containing those 2 modular spaces, or slightly modification of those. And there is a C star action of this modular space, depicted as the blue flows here. And there are the fixed loci, or the 2 moduli in 2 chambers, and some special terms in the middle. They are called correction terms. And these correction terms, so the C star action on this master space, on this modular space, so they act on the universal curves acting on this special, these P1s. And these P1s are precisely the P1 drawn here. The quasi-map is precisely this kind of constant quasi-maps. And the localization basically formula picks up the I function term. So in a nutshell, that the Walker formula just said that this invariant minus this invariant is some invariant here, but you remove this rational tail, but insert some formula coming from the I function I wrote down before. Okay. Anyway, so the whole story works without any change to more general GIT quotients. So not all GIT quotients, but special kind of GIT quotients. So if X is let X be a GIT quotient satisfying that G is a reductive group and V is a affine scheme, not very singular. And the most restricted part is that the stable locus and the semi-stable locus is smooth and not empty. For example, this includes all these toric varieties, Nakajima, type A Nakajima Q varieties. So for this kind of target space, quasi-maps can be defined. So recall that a map to this quotient stack is equivalent to a principal G bundle P over C together with a G equivalent map from P to V. So V has a G action. And this is again equivalent to a section of the bundle associated P, but you replace every fiber by a copy of V via this G action. So it's the Borel construction. So for example, you can write P4 as a quotient of C5 mod C star. And in this case, a principal C star bundle is just equivalent to a line bundle L. And the associated V bundle, V is a C5. So it's nothing but the total space of L, 5 copies of L. So a section of this bundle is equivalent to previously the 5 sections of this line bundle L. Okay. And if you consider a hypersurface instead of project space, you can replace this affine space by the affine cone of X. And base points and degrees generalize to this setting. For example, if U is a section, then the base points are the sections or the locus where the section hits the unstable part of V. And degree is, to define degree, just need a line bundle, and there's the canonical one, just the GIT polarization. Okay. For example, in the PN or hypersurface case, the origin is the only unstable point. So the base point just means that all the sections vanish simultaneously. Okay. So, okay, so in this more general setting, I want to talk about some recent applications. So the first is that the GS0 Gromfin invariance of orbifolds. This is a joint work with Felix Yanda and Nawaz Sultani. And also the Krapin resolution conjecture for this orbifolds is a joint in progress with Yunfeng Jiang. And the second part is the part of GS1 Virasoro conjecture for completed intersections. And it's joined with Shuai Guo and Qingsheng Zhang. And the second one is almost finished. Okay, let me talk about the first one. So let's consider, for example, this this orbifold hypersurface. So this is a degree 7 hypersurface inside the P11113. So the right-hand side, I think of this as a orbifold or Deligne-Manifold stack. And because, so 7 doesn't divide, so 7 is not divisible by 3. So the hypersurface cannot avoid the orbifold point 0, 0, 0, 0, 1. So the hypersurface always contains some orbifold point, some B mu 3. And in orbifold covariance theory, the right way to count curves is to not only remember where the mark point is sent to, but also remember this monodromy data at the mark points. So one take the chain-run orbifold cohomology of X7. This should be used in place of the Euro cohomology. So the chain-run cohomology is just by definition, the Euro cohomology of the inertia stack of X7. So the inertia stack is a copy of this X7. There's an orbifold point together with 2 additional points corresponding to the 2 non-trivial automorphism of this marking. Okay. So, and the grading here, the cohomology here, their grading are shifted due to the action, the group action. So if you work out the definition, you see that the H2 is actually 2-dimensional. So one coming from the divisor class on this X7, and the other coming from one of those mark points. So if it's monodromy, a third. Okay, so why is the right thing to think about? One's motivation that, so this cohomology behaves like it has two independent curve classes. It's the same as its Krapin resolution. So the Krapin resolution, X7 tilde, the right-hand side should be X7. So it can be described as a hypersurface in some variation of GIT of this guy. But anyway, so they have the same cohomologies if you use the chain-run cohomology. But the ring structure are different. So one has to use some like curve counting to correct this discrepancy in the product of this cohomology. Okay. So the Krapin resolution picks up some additional like divisor coming from this singular points. So upstairs they are like H2 is 2-dimensional, and downstairs if you use this chain-run cohomology, taking into consideration this monodromy, you also get this 2-dimensional cohomology. And so to compute this Gromov invariance, we think of this as a hypersurface inside this weighted project space, but we write this project space as some GIT quotient of this, not C5, but with additional copy of C and additional copy of C star, with the weights given by this matrix. And you choose the GIT stability condition such that the last copy of this coordinates is never 0. So if you take the GIT quotient, you see that the last copy of C, you remove the origin, and it cancels with this additional C star. So there's no change in the GIT quotient. But in terms of quasi-maps, we're considering the whole like stack quotient. We're allowed to hit this unstable locus in a controlled way. So for quasi-map theory, so it does make a difference. And you just run this quasi-map wall crossing for this GIT quotient, it gives you the mirror theorem. You see that there are 2 copies of C star, so you have 2 line bundles, you have 2 degrees. So this matches this chain-run cohomology of being dimension 2-dimensional, and which determines all the GN0 Gromov-Fini invariance. And we need to compare this with some similar computation for its Krappin resolution to verify the Krappin resolution conjecture. And then the next one is the Virasoro conjecture. So it's very complicated. The statement is very complicated. So it's Virasoro constraints is a system of differential equations satisfied by the four general Gromov potential. And when X is a point, this is the famous Witten conjecture and proved by Kontsevich. And afterward, there are also many other proofs, of course. But when X is like Pn, for example, then it has a big torus action, so the quantum cohomology is semi-simple. So using the torus action, it can be compared with the theory of its fixed points. So it can be reduced to this point case. But in general, in the so-called non-semi-simple case, this is widely open. And so we considered the GS1 invariance. For technical reason, we can only consider part of the GS1 invariance. It is all the GS0 invariance for some target spaces, but not all. For hypersurface in project space or complete intersection in project space. And so the main difficulty is that for GS1 invariance, so recall that previously we have the mapping space into X and mapping space into Pn. And in GS0, so this is cut out by a section of some vector bundle. But in GS1, it's no longer true because if you compute the cohomology of the pullback of O, like say OL. L is the degree of the hypersurface. So this is not constant. But there's no cohomology and base change. It doesn't form a vector bundle because it might have H1. And H1, it appears precisely when this happens. So this is Pn, and we have a GS1 curve. So the net line bundle on GS1 curve can have non-vanishing H1 only when the line bundle is trivial, right? So the only bad thing happens is that when the GS1 component is contracted to a point. So all the degree are on this rational tails. So using these quasi-maps, we can get rid of these rational tails. So all the degree come back to the GS1 components. And using that, we can compare that theory of the complete intersection to the theory of project space. And of course, that's a geometric reason why we can do this, but the actual computation is still very involved because we have to use some like quantization on this Pn, and use two wall crossings to go back and forth between them and obtain the proof of the part of GS1 invariant Virasoro conjecture. Okay, I'll stop here. Thank you.
Are there any questions or comments?
Yes.
Oh, please.
I guess I have two questions.
Okay.
Is there a log?
In log by I can't remember the names. Young people in Europe, they have some quasi-map, log quasi-map theory, but I haven't thought about the wall crossing yet.
Okay.
Sure.
Any other questions? if no, let's thanks Bill again.
All right, thank you.
The last speaker this afternoon is Professor Zhi Weizheng from Tsinghua University. The title of his talk is Commensurability among the Limostol monogamy groups and the transformation relations among hypergeometric functions. Let's welcome.
Thank you for the introduction, and it's my great pleasure to speak in this big conference. I have reported this talk about 10 days before in Sanya, so if you already listened to it, I apologize for that. It will be the same talk, actually. And today I'm going to talk about comparability relations among the Limostol monogamy groups and about some transformation relations among hypergeometric functions. So let me start with a very old subject called hypergeometric functions. So in very early time, Euler introduced hypergeometric functions, which is defined by this so-called hypergeometric series. So this series, so here A, B, C is just A, M, B, and C is just some generalization of the factorial of a positive integer. And this series is absolutely convergent on the unit disk. And one can extend it as a meromorphic function on the whole complex plane and even on the Riemann sphere. And this function satisfies a second-order differential equation in this written as this. And this ODE has singular points at 3 points. So first, it has also has this integral representation. It can be written as such integrals. Okay. And this ODE has 3 singular points at 0, 1, and infinity. At points not in this 3 points, when you have the solution, you can extend the solution, and you can go around these 3 singular points and go back. Then you get different points in the solution space. So this gives you the so-called monogamy representation. So here minus these 3 points from the Riemann sphere, and first you can fix 1 point and you look at the value of the solutions at this point, and then you can extend this via the ODE. Then you can go back, then you get this representation. So you get the representation from the fundamental group of E1 minus 0, 1, infinity to PGL to C. And Schwartz had systematically studied this construction, and he gave criterion for when the monogamy group, which is the image of this monogamy representation, is finite and when it is discrete. Okay. This is a very old and classical and also a very beautiful subject. And later people, so I mentioned discreteness. So Schwartz's work was later extended by Mostol and some other people, and there is some very precise description when this monogamy group gamma is discrete. So here is the criterion, and there is actually classification. When it is discrete, it is actually essentially a triangle group, which is just a group generated by reflections about the 3 sets of a triangle. The triangle can be in either the sphere or the Euclidean space or also, when you have a discrete group, you study when it is whether it is arithmetic or not. So arithmeticity means the discreteness actually comes from the discreteness of Z in the real field. So like GL and Z is arithmetic in GL and R. Also, for other B groups, we can have the similar notion. And Takeuchi classified all arithmetic and triangle groups. And this is a key notion we are going to talk about in this talk, comparability. So we call two subgroups in one ambient group G called comparable if they are essentially the same up to conjugation, which means if you conjugate this gamma 1, then you look at the intersection of the conjugation of gamma 1 with gamma 2, and then you obtain subgroup of finite index in both two groups. And we will see for a triangle case, this is actually can be seen geometrically. So you have you can also have similar notion for the triangles. And then we are going to look at a higher dimensional case. So here we have P1 dimension of P1 is sorry, not P1. So not P1. Here we have two solutions, and they go to PGL 2C, and you can see PGL 2C to be it is acting on CP1. Okay. Here, the dimension 1 is the space where this PGL 2C is acting. And then we look at the general case. So if you have more variables and can be more than 1, then you can also look at such an integral. So I did not write down the hypergeometric series for this, but there are also such series. And now we stick to this integral representation. Then you can look at the monogamy representation, which is a map from the fundamental group of the GIT quotient of this. So you look at a tuple of n plus 3 points on P1. You ask them to be distinct, so you need to minus all the diagonals. Then you take quotient by PGL2C. This is a modular space we are going to consider, and you can generalize the monogamy representation displayed before. It is this row from pi 1 of this GIT quotient to PGL n plus 1C. And here, for the choice of this differential form, there are these mu1 to mu n plus 3. So these are the weights. And we consider the case when the sum of these weights is an integer. And how does n mean? How does n mean? N mean n is smaller than 2. Yeah, you are correct. So this quotient does not depend on mu1 to mu n plus 3. This representation does depend on, and also if you consider the compactification of it, then this mu1 and mu n plus 3 gives you the linearization when you study the GIT quotient. So for different tuple of weights, the compactification are different and the representation are different. But this generic part with GIT is the same. Euclidean case, spheral case. The richest cases are given by hyperbolic case. And in Schwarz classification, when the triangle, when the monogamy group in dimension 1 case are discrete, then they are triangle groups. And when you are in the hyperbolic case, then they actually act on the Poincare disk, which is given by a Hermitian form on C2 with signature 1, 1. And you look at the positive lines, then they form the Poincare disk. These are actually hyperbolic triangles acting on Poincare disk, or equivalent, say you can regard them as some group acting on the up half plane. Okay. And in the general case, if you have more variables, so when n can be larger than 1, so this Poincare disk, which is dimension complex dimension 1, will be replaced by higher dimensional complex hyperbolic ball of dimension n. Here, in this case, when we write this, it usually means this n is at this 2. But the case when n is equal to 1 is just the classical case. Here, then, this monogamy representation in row will live invariant on Hermitian form of signature 1n. And once you have such a Hermitian form, which we call a unitary Hermitian form, then you can consider the space of positive lines in the n+1 dimensional complex space. So here positive means that any non-zero representative has a positive norm with respect to this Hermitian form. Then this monogamy group of gamma mu, which is the image of rho. It will be a subgroup of this PU1n. PU1n is just the automorphism group of Cn+1 with unitary Hermitian form. Over C, we just get this PU1n. But there will be choices of this H when we consider H as a Hermitian form over some smaller fields. So if you consider it over C, then there's no choice. Okay. It is determined by this signature. But from the definition of, you are given this tuple of weights mu1 to mu1 plus 3, then you can consider some descent of this Hermitian form to some small field, some smaller field like the field Q and square root of -3 or Q of square root of -1. So and we will see that. And the theory by Deligne-Mostel and Thurston, they study when this generalized monogamy group is discrete. So in general, this monogamy group can be dense, or can be very complicated. But we are interested in the case when it is a discrete subgroup of PU1n. Okay. They obtain an equivalent condition called sigma INT condition, which is a very simple numerical conditions on these weights, mu1 to mu1 plus 3, but I did not write it down. And they found there are only finitely many cases when this monogamy group gamma mu is discrete. Here is another point of view. Deligne-Mostel and Thurston, they have independent approach, and the Thurston's approach is more geometric. Deligne-Mostel's approach is more about calculation, about homology of shift and modular spaces. Thurston's approach, you can see it. It is like this. So here, we can consider a projective form, and once you have projective form, a meromorphic projective form, you look at its poles, then the order of the poles will form can be regarded as a metric on the sphere. And the pose gives you some cone vertices. And here, x1, 2, here is an example when n is equal to 2. And you can link this cone vertices via some straight line with respect to this metric, and you can develop this sphere into a polygon. And the area of this polygon is actually this machine form H defined before. So this is the big idea by the geometric approach by such manner, and really see something. And the angle of this xi as a cone vertex is given by the width. Okay. So there are many motivations why we study a subgroup of P1 and why we care about its discreteness and arithmeticity. First, we recall by Delimostro and Thurston, there is classification of discrete subgroups of P1 arise where this finitely many points on P1 with weights. And there are totally 104 cases by their classification. In the case when n is at least 2. The case n is equal to 1 was already classified by H. And among these examples, they prove that once they are discrete, then they must be lattice, which means the quotient of the hyperbolic bow by this discrete group has finite volume with respect to the hyperbolic metric. And there are examples among them which are non-arithmetic. Most of them are arithmetic, but some are non-arithmetic. From their constructions, I think they are the first group of people who really found non-arithmetic lattices in PU1, 2, and PU1, 3. Here is the history. So this is a very important. There are some very important results. So by many people, you can see here. So we want to know about the structure of discrete subgroups of Lie groups, and when you know a subgroup is a lattice, you ask whether it must be arithmetic. And in most cases, the answer is yes. And this is Margulis superrigidity theorem. And also, some cases are solved by other people. But there are two cases very special. One is this case, so they are so-called the REP1 cases. The case O1 and people know that for each n, there are infinitely many variability classes of non-arithmetic lattice. And the case we are interested in is PU1, which is still widely open actually. So for case n equal to 2 and 3, the Delimostro and Thurston provides some non-arithmetic lattices. And now there are and the most recent result is by the Parker and Popper in 2014. They found that there are now the example plus the Delimostro and the Thurston example, they are now totally 22 classes in dimensional 2. And there are two cases which are non-arithmetic and not comparable to each other. One is given by the Delimostro and one given by Kovenberg, Kaplan, and Ryan in dimension 3. So we up to that there are 22 non-arithmetic lattices in PU12 and two non-arithmetic lattices in PU13 up to commutability. These are all we know now. And for dimension larger than 3, we do not know any example. And so it is rather open. If you can find one example, then it's perhaps. Also, we do not have any bound on this. So if you can prove that in certain dimension, such example should be only finitely many, it's also a very, very big result. This is one of the motivation why we study these constructions. Okay, and we see here we have the force and we have the monogamy group, and in some interesting cases they are discrete, and then you can look at the quotient. You can study the geometry of this Bow quotient, and also one can study their compactations and so on. And from the algebra geometric point of view, this motivation for studying these Bow quotients, which has modular meaning. Here are some interesting examples of some algebra varieties whose modular space can be realized as compact hyperbolic Bow quotient, where they appear in map. So the Limassol and Thurston gave a series of this. There are totally 104 examples, and I did not mention that for all these cases, that the Limassol and Thurston, the modular space has a dimension at most 9. So 9 is the maximal possibility for the dimension. And Kondo studied two very interesting examples in around 2000. So the model of genus 3 curve. Generically, such a curve is a quartic curve in P2, and one can study an associated cyclic cover of P2, which is a quartic surface, which is a K3 surface. Then you can study, you can look at the Hodge structure of this K3 surface together with action of cyclic group of order 4. And you can look at the model of such Hodge structure with action. It is actually some data. This data actually leads to a point in a 6-dimensional ball. And if you look at the corresponding ball quotient, you find it is a variety naturally defined over this Qi, which is called Gaussian field. This means that the corresponding Hermitian form defined from the setup has coefficients naturally in this field. Then also for genus 4 case, which we will give more details later, one get a 9-dimensional Bow quotient over this essence complete, the square root of -3. And this case, you see it has dimension 9. It is actually comparable to the maximal case in the Limassol theory. In the Limassol theory, there is a unique case which has dimension 9, which is maximal. And it is comparable to the modular, the modular of genus 4 curves. And also there are two very famous examples for cubics. So a model of cubic surface is a dimensional 4 Bow quotient. And the model of cubic threefold is a dimensional 10 Bow quotient. So this dimension exceeds the dimension of the largest Limassol, which is 10, one larger than the 9. And also, there are some general construction. You can look at model of some polarized Taylor manifolds with some group action. If the group action has some, so if reduce the character for the action on this H20 of the hyperpolar manifold, which is complex line, has some non-real number. Then you can consider the whole structure with some non-real action. Then you can get some data with full quotient. So here I explained that for this case, Condo's case, one has some construction called cyclic cover, and Professor Sheng Mao, Xu Jinxin, and Zuo Kang, they have a systematic study of cyclic covers for the case projective space. So here's an example. If you look at a triple cover, which is cyclic cover of degree 3, Y of P3, branching along a generic 6 hyperplanes in position, then Y is actually orbital, which admits a Krafton resolution. And since it's a triple cover, so there is action of the cyclic group of all the 3 on the third cohomology of Y. And you can decompose this cohomology. And here is the decomposition. And here, K is the tautological capital of 0 over 3 group. And here is the calculation. So there's the Hodge numbers 1 and 3. And then you fix this. So when you vary this 6 hyperplane, the topology of Y does not change. The action does not change. So here the numbers does not change. And this character space H3 chi Y does not change. It is dimensional 4 space which has a Hermitian form. And Hermitian form has signature 1 and 3. And this H3 0 by Riemann Hodge-Riemann bilinear relation, it corresponds to a positive line. So when you vary these 6 hyperplanes, the only thing changing is the position of this H3 0, or some, or you can say from the period side, the positive line is changing. So you can map the GIP quotient for this 6 hyperplane to the period domain, which is 3-dimensional Bode quotient. So here the domain is 3-dimensional Bode quotient, and they prove that here one has global Torelli theorem, which means this period map is injective. And this case is also closely related to the Limonov example. And the example where you have 6 points on P1 with equal weights. And in their paper, they also, after they studied the general case where one has cyclic cover of Pn branching along hyperplanes. And they prove that, so here n equal to 3 is just one of the examples. When n is equal to 5 and 9, they also obtain arithmetic quotients, Bode quotients. But both of them are comparable to cases in the Limonov. And for n larger than 1, does not get discrete group. So for Condo's case of genus 4 curves, here is some more details which we are going to generalize. Condo consider non-happy elliptic curve of genus 4, which can be realized as a curve in P1 cross P1 of by degree 3, 3. So if you take triple cover of P1 cross P1, then you also get a surface has action for simply cover of all three, which we call mu3, and then you have some similar construction. Then you get Ball quotients comparable to the maximal Ball quotients in the Riemann-Stieltjes theory. And one observation is, if you do not study a generic curve of band-grid symmetry, instead you consider degeneration of them. You allow you allow there are singularities, and you allow there are multiple components. You can also have do this construction like the work by Shen Xu. You can consider the case when the branch locus is degenerate. So here they study six type plates. Generically, they are so-called simple normal crossing divisor. So here, if you degenerate the branch loci, then you also get Ball quotients, but they are smaller Ball quotients, so dimension will decrease. So how about there are more pieces of P1? So here is one joint work with Cheng Yu. Yeah, we consider a single covers of actually we consider a single cover of P1 to the power n. So here is only the result for the case n equal to 3. If you look at a triple cover of P1 cross P1 cross P1, and you allow the branching locus to be simple normal crossing divisors of total degree 3, 3, 3. Okay. Then when this DI varies, you have a family of Triennial orbitals, and you can look at GIP quotient, and you have the modular space. On the other side, you have the action of mu3 on the third cohomology of Y. Then you have character decomposition, and then you can look at the positive line generated by the volume form of this Triennial orbital in the corresponding character space. Then on the field side you have a field domain, but the problem is when this field domain is actually a compact hyperbolic ball. So you want some structure like this. You want this 1, 3 by 0, 0. After all, if you have a three-dimensional Triennial and you have action of mu3, here may be something non-zero, which one maybe non-zero. So our result is when the branching locus are of this type for their refinements, then the field domain is actually a complex Ball quotient. And the first case was well studied before by many people in many papers, and the last three cases are new cases we found, and this gives us Ball quotients of dimension 9, 9, 7, and 6. One remark is in these cases, in the last three cases, we still do not know whether the global triangle holds. So you only have the field map from the module of this branching locus, or the module of this Triennial orbital to this Ball quotients, which are proved to be arithmetic, but we do not know whether it is injective. Okay, Limassol theory, in 1980s, the Limassol and the Limassol student Sauter, they studied the question of the question, so found comparability relations among the Limassol data. So after this, these pairs were essentially found by some computer investigation. The Lin and Limassol had a book on this of the results. It's very complicated to obtain this. And once you know some some tuples are comparable, then you want to know are there any more relations? So the question is, you also want to know which two are not comparable. Okay, or I can say in this way. So we want to classify all comparable relations among the Limassol data. These are work by Kapis Mura and Mark Muller. They classify comparability classes for non-arithmetic figures. For PU13, there are nothing to do. So for PU12, there are some non-arithmetic lattices, and then they found some comparability invariance. So the invariance they are using one is adjoint trace theory for this monogamy group. So this monogamy group is a subgroup of P1, and then you can study the adjoint trace of them and study the field generated by this trace. And some geometric invariance. There are Chern numbers. These are works. And here is the main results in this part. So last year with we have some other geometric approach to reprove the Limassol and Sauter's relations. So here are their relations. And also we found some new relations in dimensional 3. And for dimension larger than 3, we found some finite pairs of comparability relations. And one remark is we do not need to restrict ourselves to the discrete form. So even our monogamy group are non-discrete. You can also talk about comparability because they are subgroup of P1. And so actually these are infinitely many relations. So because you can involve all the cases, not only the discrete. So the approach is the idea for our group. Go back to our previous result about this triple cover of P1 to power n as Calabi-Yau orbitals. But we need to generalize that construction. So now we do not ask the cover to be Calabi-Yau orbitals anymore. We only want the cover has Calabi-Yau type hot structures. So we do not ask the branching locus to be simple normal class. We allow the divisors to have multiplications, and the cover can be written as this. So the affine equation can be given by y to power d is equal to the product of this, and each fi defined an irreducible divisor in P1 to the power m. And you can still consider the homologous y together with action of a cyclic group of order B. And there are some conditions for this B and A1 to AK to ensure that you have a Calabi-Yau condition, which means it's H M0 in this eigenspace as dimension 1. And you can denote by omega one generator for this one-dimensional space. And if you integrate this omega over some cycles, you can get some multi-value functions on this space. Okay, so here are the conditions we need to ensure the Calabi-Yau condition. These are some homologic applications. So here I just give the results. And so once you check that your width and the degree of this satisfy this condition, then we are in a good situation. And together with some more condition on the singularity types, we can prove some it will lead to some comparability relations in this way. So here we only consider two pieces of P1. And you have this field cover Y, which is a surface. And it may not be a Calabi-Yau surface. It can be a surface, but with Calabi-Yau type homology. And this surface has two projections to each P1. And you can consider the discriminant set for the two projections. And they consist of n plus 3 points both. And also here, so you can consider some local system induced from these projections, and then you can consider the monogamy group for the local system around each discriminant point. Then you can calculate the corresponding multiplication. This gives you two data in the Limon-Stowe theory. So here is one example. Here's one example. There are 4 components for this function divisor, and you look at projections to each side, and to the left side there's 4 intersection points. Give you 4 discriminant points, and the divisor D2 will go to 1 point. So there are 5 discriminant points. And if you go down to P1 Y, then D3 and D4 will go to 2 points, and the intersection of D2 and D1 here will go to 1 point, and the projection of D1 to P1Y will have two discriminant points, because it is a 2-to-1 couple. You can calculate by Bool's formula. Okay, and you can study the relation of the modular spaces. One is the modular of the surface, and you can also study the modular of these tuples of discriminant points. Okay. Then you have 2 such maps from modular of surface and to the modular of the finite sets on P1. And we calculate the indices, and they are both generically finite under some condition. And this gives you, this eventually leads to comparability relation between the two tuples given by the projection. So here is one example, and this will recover one of the Limon-Stowe and Sauter's relation. And there are also other graphs, so you can imagine there are other graphs, and for each graph we can have some relation like this. I have no time, and okay, let me mention this only very quickly. So similar thing for hypergeometric function. So for hypergeometric function, here's some history, some work from variation type U1. You can see such transformation relations. And the classical idea to prove this is to prove that this satisfies the same ODE. And they are inspired by our work on comparability relation among the Limon-Stowe theory. So one idea is we can integrate this volume form on the caviar type surface over some real circle. And we can integrate it from different directions. So we can integrate over dx, then integrate over dy, or the other way around. And eventually this will lead to some so for this case it will eventually lead to transformation relation first found by Gosset. And there are also other choice of the cycles and the choice of the graph. There will be other relations. And this is a new type of proof of such relations. It's some binary type proof of such relations. This is an ongoing project with Chenglong Yu and Wang Shihao. Wang Shihao is my student. Okay, here yeah, so let me just go through the final result. So in our paper, we also fully classified all comparability relations. So we proved that the 104 Limon-Stowe tuples actually form 38 comparability classes. And the idea is the non-arithmetic case was already solved by Kapis-Muller and Mark-Muller. But here we also reformulated it in a more concise way based on some the ideas are essentially something not completely new. So one can look at some the signature of these relating forms under some general conjugation and called by Barak operator signature spectrum. And also you can look at the defining field for parallel divisors of the Limon-Stowe quotients, which are some abelian varieties. And also for arithmetic case, one need to study the explanation forms in this. They obtain a formula to calculate the determinant, and which will lead to the final result. Okay, thank you. I will stop here. Sorry for.
Thank you very much. Are there any questions or comments? About the Limon-Stowe lattice, they give some examples.